Welcome to our journey to the edge of the universe. Today, we'll explore the vast expanse of space, from the birth of the cosmos to the farthest reaches of what we can observe. This guide will take you through the key concepts, discoveries, and theories that shape our understanding of the universe's boundaries. Imagine a time when the universe was born, a moment known as the Big Bang. This monumental event set everything in motion, creating the building blocks of matter and energy that eventually formed stars, galaxies, and planets. We'll delve into the details of the Big Bang theory and how it explains the origins of our universe. As we move forward, we'll discuss the expansion of the universe, a phenomenon that has intrigued scientists for decades. Hubble's law revealed that galaxies are moving away from us, indicating that the universe is expanding. We'll explore the evidence behind this expansion and what it means for the future of the cosmos. To understand the vast distances in space, we use a cosmic distance scale. This includes measurements like light years and parsecs, as well as tools such as standard candles and redshift. These methods help astronomers map the universe and determine its size and structure. The observable universe is the portion of the cosmos that we can see and study. It's limited by the speed of light and the age of the universe. We'll look at how astronomers observe this vast region using telescopes and satellites, uncovering incredible phenomena along the way. Beyond the observable universe lies the concept of the cosmic horizon. This boundary marks the limit of what we can ever hope to observe. We'll discuss the differences between the event horizon and the particle horizon, and what these terms mean for our understanding of the universe's limits. Theoretical boundaries of the universe take us into the realm of speculative science. Various models propose different shapes and sizes for the universe, from flat and infinite to closed and finite. We'll touch on theories like the multiverse, string theory, and quantum mechanics at cosmic scales. Dark matter and dark energy are two mysterious components that dominate the universe. Dark matter helps hold galaxies together, while dark energy drives the accelerated expansion of the cosmos. We'll explore what we know about these elusive substances and their impact on our understanding of the universe. The large-scale structure of the universe reveals a cosmic web of galaxies, clusters, and voids. This intricate arrangement shows how matter is distributed on the grandest scales. We'll look at how these structures formed and evolved over billions of years. Finally, we'll touch on the enigmatic black holes, regions of space where gravity is so strong that not even light can escape. Black holes challenge our understanding of physics and represent the ultimate cosmic boundary. We'll discuss their types, properties, and significance in the universe. The Big Bang theory is the cornerstone of modern cosmology, describing the origin of the universe. It suggests that the universe began as a singular, incredibly hot and dense point around 13.8 billion years ago. This singularity then rapidly expanded, leading to the universe we know today. In the first few moments after the Big Bang, the universe underwent a period of rapid inflation. During this time, it expanded faster than the speed of light, smoothing out any irregularities. This inflationary period set the stage for the formation of matter and the large-scale structure of the cosmos. As the universe expanded, it cooled down, allowing particles to form. Quarks combined to create protons and neutrons, which eventually formed the nuclei of the first atoms. This process, known as nucleosynthesis, occurred within the first few minutes after the Big Bang. The universe continued to cool, and about 380,000 years later, electrons combined with these nuclei to form neutral atoms. This period is known as recombination, and it allowed light to travel freely through space for the first time. This relic radiation is what we observe today as the cosmic microwave background. The cosmic microwave background, or CMB, is a critical piece of evidence supporting the Big Bang theory. It's a faint glow left over from the early universe, providing a snapshot of the cosmos at a young age. The CMB was discovered in 1965 by Arno Penzias and Robert Wilson, who won the Nobel Prize for their work. Detailed measurements of the CMB have revealed tiny fluctuations in temperature. These fluctuations correspond to regions of slightly different densities, which later grew into galaxies and clusters of galaxies. Studying the CMB helps scientists understand the early conditions of the universe and its subsequent evolution. The Big Bang theory also explains the abundance of light elements in the universe. Observations show that hydrogen, helium, and lithium are present in amounts consistent with predictions from Big Bang nucleosynthesis. This agreement between theory and observation is a strong endorsement of the model. As the universe continued to evolve, the first stars and galaxies began to form. Gravity pulled matter together, leading to the formation of these early structures. The light from these first stars ended the cosmic dark ages, a period when the universe was filled with neutral hydrogen gas. These first stars, known as population 3 stars, were massive and short-lived. They produced heavy elements through nuclear fusion, which were then dispersed into space when the stars exploded as supernovae. This enrichment of the interstellar medium allowed subsequent generations of stars to form with heavier elements. Galaxies grew and evolved through mergers and interactions. Over billions of years, these processes led to the diverse array of galaxies we see today. The Milky Way, our home galaxy, formed through such mergers, accumulating stars and gas from smaller galaxies. The discovery of the expanding universe was a pivotal moment for the Big Bang theory. Edwin Hubble observed that galaxies are moving away from us, with their speed proportional to their distance. This observation led to the formulation of Hubble's law and provided strong evidence for an expanding universe. Hubble's discovery implied that the universe had a beginning, which could be traced back to the Big Bang. This challenged the previously held steady-state theory, which posited that the universe had no beginning or end. The expanding universe model became a cornerstone of the Big Bang theory. The Big Bang theory also predicts that the universe will continue to expand. Observations of distant supernovae have shown that this expansion is accelerating, driven by a mysterious force known as dark energy. Understanding dark energy is one of the biggest challenges in cosmology today. While the Big Bang theory is widely accepted, it doesn't answer all questions about the universe's origin. For instance, what caused the initial singularity and what happened before the Big Bang? These are areas of active research, with theories like quantum gravity and string theory offering potential insights. The Big Bang theory has profoundly impacted our understanding of the universe. It has provided a framework for studying cosmic evolution and the formation of structures in the cosmos. As we continue to explore the universe, new discoveries will further refine and expand our understanding of its origins. Cosmic inflation is a crucial concept in understanding the early universe. It describes a period of extremely rapid expansion that occurred fractions of a second after the Big Bang. This exponential growth set the stage for the universe's large-scale structure. During inflation, the universe expanded by a factor of at least 10^26 in less than a trillionth of a second. This dramatic expansion smoothed out any initial irregularities and homogenized the observable universe. It explains why the universe appears so uniform on large scales. One of the main drivers behind the theory of inflation was the horizon problem. This problem questions how regions of the universe so far apart could have such similar temperatures. Inflation solves this by suggesting that these regions were once close together before the rapid expansion. Another issue addressed by inflation is the flatness problem. Observations show that the universe is remarkably flat, meaning its overall geometry is very close to Euclidean. Inflation stretched any initial curvature of the universe to near flatness. Inflation also provides a mechanism for the generation of primordial density fluctuations. Quantum fluctuations during the inflationary period were stretched to macroscopic scales. These fluctuations eventually grew into the large-scale structures we see today, like galaxies and clusters. Alan Guth first proposed the idea of inflation in 1980, introducing a new field called the inflaton field. This field drove the rapid expansion and then decayed, releasing energy that reheated the universe. This reheating led to the formation of particles and radiation. The inflaton field's potential energy is key to understanding inflation. During inflation, the universe was dominated by this potential energy, causing rapid expansion. As the inflaton field settled into a lower energy state, inflation ended and the universe transitioned to a more normal expansion rate. Inflation theory has made several predictions that have been confirmed by observations. One such prediction is the nearly scale-invariant spectrum of primordial fluctuations. This means that the fluctuations are almost the same on all scales, which is supported by data from the cosmic microwave background. The theory also predicts a specific pattern of polarization in the cosmic microwave background. This pattern, known as B-mode polarization, is a signature of gravitational waves generated during inflation. Detecting these patterns is a major goal for current and future cosmological experiments. Despite its successes, inflation is not without its challenges. One of the main issues is identifying the exact mechanism and nature of the inflaton field. There are many different models of inflation, each with its own implications and predictions. Some theories suggest that inflation may have occurred multiple times, creating a multiverse. In this scenario, our universe is just one of many bubbles that underwent inflation. This idea, while speculative, has profound implications for our understanding of the cosmos. Another intriguing aspect of inflation is its connection to high-energy physics. The conditions during inflation involve energies far beyond what we can achieve in particle accelerators. Studying inflation can therefore provide insights into fundamental physics and the early universe. Inflation also has implications for the ultimate fate of the universe. While it explains the early rapid expansion, it also raises questions about the long-term behavior of cosmic expansion. Understanding how inflation ended could offer clues about the future dynamics of the universe. Researchers continue to develop and test new models of inflation. Observations from space telescopes and other instruments provide critical data to refine these models. As technology improves, we may uncover more details about this pivotal period in cosmic history. The study of cosmic inflation is a vibrant field that intersects with many areas of physics and astronomy. It not only helps explain the initial conditions of the universe, but also opens up new avenues for exploring the fundamental laws of nature. As we probe deeper into the mysteries of inflation, we edge closer to a more complete understanding of the universe's origins. The formation of the first elements, known as Big Bang nucleosynthesis, occurred within the first few minutes of the universe's existence. During this period, the universe was hot and dense enough for nuclear reactions to take place. These reactions produced the lightest elements, hydrogen, helium, and small amounts of lithium and beryllium. As the universe expanded and cooled, protons and neutrons began to combine to form the nuclei of these light elements. Most of the matter in the universe was hydrogen, with about 25% helium by mass, and trace amounts of other light elements. This primordial abundance is a key prediction of the Big Bang theory. The conditions for Big Bang nucleosynthesis were precise and short-lived. If the universe had expanded slightly faster or slower, the resulting element abundances would have been different. This delicate balance underscores the fine-tuning of the early universe. During the first few minutes, temperatures were around 1 billion degrees Kelvin. At these temperatures, nuclear fusion could occur, similar to processes in the cores of stars. However, the universe's rapid expansion soon reduced temperatures and densities, ending nucleosynthesis. One of the most important reactions during this period was the fusion of protons and neutrons to form deuterium. Deuterium, a heavy isotope of hydrogen, then fused to form helium. This sequence of reactions determined the final amounts of hydrogen and helium. The abundance of deuterium in the universe provides critical evidence for Big Bang nucleosynthesis. Deuterium is easily destroyed in stellar interiors, so its presence in the universe points to its primordial origin. Measurements of deuterium match the predictions from Big Bang nucleosynthesis calculations. Helium-4 is another key product of Big Bang nucleosynthesis. Its abundance is well understood and matches observational data from various sources. The consistency between observed helium levels and theoretical predictions supports the Big Bang model. In addition to hydrogen and helium, trace amounts of lithium were produced. The observed abundance of lithium is lower than theoretical predictions, a discrepancy known as the cosmological lithium problem. This remains an open question in cosmology. The formation of these light elements set the stage for the later development of stars and galaxies. The hydrogen and helium produced during Big Bang nucleosynthesis became the raw material for the first stars. These stars would go on to create heavier elements through stellar nucleosynthesis. The light element abundances also provide a window into the conditions of the early universe. By comparing observed abundances with theoretical models, scientists can infer details about the universe's density and expansion rate during its first few minutes. This helps refine our understanding of the Big Bang. Observations of light element abundances come from a variety of sources. These include measurements in ancient stars, gas clouds, and the intergalactic medium. Each provides a piece of the puzzle, contributing to a coherent picture of Big Bang nucleosynthesis. Big Bang nucleosynthesis is a well-tested theory, but it also has implications for other areas of physics. It intersects with particle physics, nuclear physics, and cosmology. Studying these connections can reveal new insights into the fundamental laws of nature. Future observations and experiments aim to resolve outstanding questions, such as the cosmological lithium problem. Advanced telescopes and improved theoretical models will help refine our understanding. As we gather more data, we continue to test and challenge the Big Bang nucleosynthesis theory. The study of the first elements also informs our search for dark matter. Certain theories of dark matter predict different light element abundances. By comparing these predictions with observations, scientists can test and constrain dark matter models. Overall, the formation of the first elements is a cornerstone of cosmology. It provides critical evidence for the Big Bang theory and insights into the early universe's conditions. As we continue to explore this era, we deepen our understanding of the universe's origins and evolution. The early universe was an incredibly hot and dense environment. During the first seconds after the Big Bang, temperatures were unimaginably high, reaching up to billions of degrees Kelvin. This intense heat meant that particles were in a state of constant interaction. In this primordial soup, fundamental particles such as quarks and gluons moved freely. As the universe expanded and cooled, these particles began to combine, forming protons and neutrons. This process set the stage for the formation of atomic nuclei. Radiation dominated the early universe, filling it with high-energy photons. These photons interacted frequently with charged particles, keeping the universe opaque. It wasn't until much later that the universe became transparent to light. The rapid expansion of the universe caused it to cool down quickly. Within minutes, temperatures dropped enough for nuclear fusion to begin, leading to the formation of light elements. This period of nucleosynthesis was brief but crucial for creating the building blocks of matter. As the universe continued to expand, it entered a phase where matter and radiation were in thermal equilibrium. During this time, the density of the universe decreased, and the average energy of particles diminished. This transition set the stage for the formation of neutral atoms. About 380,000 years after the Big Bang, the universe cooled to a point where electrons could combine with protons and nuclei to form neutral atoms. This event, known as recombination, allowed photons to travel freely for the first time. The release of these photons is observed today as the cosmic microwave background. The cosmic microwave background provides a snapshot of the universe at this early stage. It reveals a nearly uniform temperature with tiny fluctuations. These fluctuations correspond to the seeds of future galaxies and large-scale structures. During the early universe, dark matter began to play a significant role. Unlike normal matter, dark matter did not interact with light, but contributed to the gravitational framework of the cosmos. Its presence influenced the formation of structures we observe today. The distribution of dark matter created gravitational wells where normal matter could accumulate. This process eventually led to the formation of galaxies and clusters. Understanding dark matter is essential for explaining the early universe's evolution. Inflation had a profound impact on the conditions of the early universe. By smoothing out irregularities and distributing matter evenly, it set the initial conditions for the Big Bang nucleosynthesis and structure formation. This rapid expansion also stretched tiny quantum fluctuations to cosmic scales. These quantum fluctuations, amplified by inflation, became the seeds for the large-scale structure of the universe. Over billions of years, they grew under the influence of gravity into galaxies, clusters, and superclusters. Studying these structures helps us trace back to the early universe conditions. The early universe also saw the decoupling of different forces. Initially, the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were unified. As the universe cooled, these forces separated, leading to the distinct interactions we observe today. This separation of forces is a key area of research in particle physics and cosmology. Understanding how and when these forces decoupled can provide insights into the fundamental laws governing the universe. It also connects the early universe to theories like grand unification and string theory. High-energy particles in the early universe included neutrinos, which played a crucial role in shaping its dynamics. These nearly massless particles decoupled from the rest of the matter early on and continued to stream through space. Observations of the cosmic neutrino background offer another window into the early universe. Research into the early universe conditions continues to evolve with new technologies and observations. Advanced telescopes and experiments, both on Earth and in space, aim to gather more data about this formative period. Each discovery brings us closer to understanding the origins and evolution of our universe. The Big Bang theory is supported by multiple lines of evidence, each reinforcing the idea of a universe that began from an incredibly hot and dense state. One of the most compelling pieces of evidence is the observation of the cosmic microwave background radiation. Discovered in 1965, this faint glow of microwaves pervades the entire universe and is a remnant of the early hot universe. Another strong piece of evidence comes from the abundance of light elements. Predictions from Big Bang nucleosynthesis match the observed amounts of hydrogen, helium, and lithium in the universe. This agreement between theory and observation supports the idea of a hot, dense beginning. The expansion of the universe, first observed by Edwin Hubble, also supports the Big Bang theory. Hubble discovered that galaxies are moving away from us, with their speed proportional to their distance. This observation suggests that the universe is expanding from an initial explosive event. The large-scale structure of the universe, such as the distribution of galaxies and clusters, aligns with predictions from the Big Bang model. Computer simulations of the universe's evolution from initial conditions provided by the Big Bang match the observed structures. This concordance strengthens the case for the Big Bang. Observations of the cosmic microwave background radiation have revealed tiny temperature fluctuations. These fluctuations correspond to slight density variations in the early universe, which later grew into galaxies and clusters. Detailed measurements of these fluctuations have provided a wealth of information about the early universe. Another critical piece of evidence is the discovery of the cosmic redshift. As light from distant galaxies travels through the expanding universe, it gets stretched to longer, redder wavelengths. This redshift provides a direct measurement of the universe's expansion rate over time. The isotropy of the cosmic microwave background radiation supports the Big Bang theory. Despite tiny fluctuations, the radiation is remarkably uniform in all directions. This uniformity suggests a common origin for the entire observable universe. Galactic evolution observed through deep space telescopes also supports the Big Bang theory. By looking at distant galaxies, we can see how galaxies have changed over billions of years. These observations match predictions from the Big Bang model about how galaxies form and evolve. The discovery of the cosmic neutrino background is another piece of supporting evidence. These nearly massless particles, which decoupled early in the universe's history, provide additional confirmation of the conditions predicted by the Big Bang theory. The consistency of physical laws throughout the observable universe supports the Big Bang model. Observations show that the same physical laws apply everywhere, suggesting a common origin. This uniformity is a fundamental prediction of the Big Bang theory. The discovery of dark matter and dark energy also fits within the framework of the Big Bang. Dark matter, which affects the gravitational dynamics of galaxies, and dark energy, which drives the accelerated expansion of the universe, are integral to the Big Bang model. Their effects are consistent with the predicted evolution of the universe. High-energy particle physics experiments provide indirect evidence for the Big Bang. Conditions created in particle accelerators, which mimic those of the early universe, support theoretical predictions about particle behavior. These experiments help validate models of the early universe. The alignment of theoretical predictions with observed cosmic background radiation patterns provides robust evidence. The observed polarization patterns in the cosmic microwave background match those predicted by inflationary Big Bang models. These patterns give insights into the earliest moments of the universe. The large-scale homogeneity of the universe is another supporting factor. Despite local variations, the universe is homogeneous when viewed on a large scale. This large-scale uniformity aligns with the expectations of the Big Bang theory. Continued observations and discoveries in cosmology consistently reinforce the Big Bang model. As new data becomes available, the Big Bang theory continues to provide a coherent and comprehensive explanation for the origin and evolution of the universe. Each piece of evidence adds to our understanding, solidifying the Big Bang as the leading cosmological model. Hubble's law is a fundamental observation in cosmology that reveals the universe's expansion. It states that the farther away a galaxy is, the faster it is moving away from us. This relationship was first observed by Edwin Hubble in 1929. Hubble's discovery was based on the redshift of light from distant galaxies. He noticed that light from these galaxies was shifted towards the red end of the spectrum, indicating they were moving away. This redshift provided the first evidence for the expanding universe. The relationship between distance and velocity in Hubble's law is linear. This means that if a galaxy is twice as far away, it is moving away twice as fast. This proportionality is represented by the Hubble constant. The Hubble constant is a crucial parameter in cosmology. It quantifies the rate of expansion of the universe. Determining its exact value has been a significant focus of astronomical research. Hubble's law can be expressed mathematically as v in h0d, where v is the velocity of a galaxy, h0 is the Hubble constant, and d is the distance to the galaxy. This simple equation encapsulates the relationship between distance and recession velocity. Measuring the Hubble constant involves observing distant galaxies and their redshifts. By determining their distances and velocities, astronomers can calculate the Hubble constant. Different methods have been developed to improve the accuracy of these measurements. One method for measuring distances is using standard candles. These are astronomical objects with known luminosities such as Cepheid variables and type Ia supernovae. By comparing their known luminosity to their observed brightness, distances can be calculated. Another approach is to use the cosmic distance ladder. This method involves a series of overlapping techniques to measure distances at different scales. Each rung of the ladder provides calibration for the next, from nearby stars to distant galaxies. Recent observations have led to some tension in determining the Hubble constant. Different methods have produced slightly different values. This discrepancy has sparked ongoing research and debate in the scientific community. Hubble's law not only supports the Big Bang theory, but also provides a framework for understanding the universe's expansion history. It implies that the universe was once much smaller and has been expanding over time. This expansion can be traced back to the initial conditions of the Big Bang. The discovery of Hubble's law revolutionized our understanding of the cosmos. It shifted the perception of the universe from a static entity to a dynamic, evolving one. This realization opened new avenues for exploring cosmic origins and evolution. Hubble's law also has implications for the ultimate fate of the universe. Depending on the universe's density and the properties of dark energy, it could continue to expand forever, slow down, or eventually collapse. Understanding the expansion rate is key to predicting these future scenarios. The concept of redshift used in Hubble's law is a cornerstone of observational cosmology. It provides a way to measure the velocity of distant objects and their relative distances. Redshift measurements continue to be a vital tool in mapping the universe. Advances in technology and observational techniques have refined our understanding of Hubble's law. Modern telescopes and instruments provide more precise measurements, enhancing our knowledge of the universe's expansion. Each new discovery builds on Hubble's foundational work. Hubble's law remains a central pillar of cosmology. It connects the observable properties of galaxies to the underlying dynamics of the universe. As research progresses, it continues to offer insights into the fundamental nature of cosmic expansion and the history of the universe. Observational evidence is crucial in understanding and confirming cosmological theories. One of the strongest pieces of evidence for the Big Bang is the cosmic microwave background radiation. This faint glow, detected uniformly across the sky, is a relic from the early universe, providing a snapshot of its infancy. The abundance of light elements such as hydrogen, helium, and lithium aligns with predictions from Big Bang nucleosynthesis. The observed ratios of these elements in the universe closely match the theoretical models. This agreement supports the idea of a hot, dense origin. Galactic redshift observations, first noted by Edwin Hubble, reveal that galaxies are moving away from us. The degree of redshift correlates with their distance, illustrating the universe's expansion. This discovery is fundamental to our understanding of cosmological evolution. Deep space surveys such as those conducted by the Hubble Space Telescope show the large-scale structure of the universe. These surveys reveal a web-like arrangement of galaxies and clusters, consistent with models of cosmic evolution from initial density fluctuations. These structures provide a map of the universe's growth over time. Type Ia supernovae serve as standard candles for measuring cosmic distances. Their consistent luminosity allows astronomers to determine distances to far-off galaxies. Observations of these supernovae have shown that the expansion of the universe is accelerating, influenced by dark energy. Gravitational lensing, where light from distant objects is bent by massive intervening structures, offers another line of evidence. This phenomenon confirms the presence of dark matter, as the amount of lensing observed cannot be explained by visible matter alone. It provides a way to map the distribution of dark matter in the universe. The distribution of galaxies and their velocities within clusters also indicates the presence of dark matter. The observed gravitational effects cannot be accounted for by visible matter alone, suggesting a significant dark matter component. These observations support theories of cosmic structure formation. The cosmic microwave background (CMB) measurements from the Planck satellite have provided high-precision data. These measurements offer detailed information about the early universe's conditions, including its composition, density, and expansion rate. The data align well with theoretical predictions from the Big Bang model. Baryon acoustic oscillations, imprinted in the distribution of galaxies, offer a standard ruler for measuring cosmic distances. These oscillations are relics from sound waves in the early universe, frozen in the distribution of galaxies. They provide independent confirmation of the universe's expansion history. Observations of galaxy formation and evolution offer insights into the universe's history. By studying galaxies at various stages of development, astronomers can trace how they evolve over billions of years. These studies align with models of hierarchical structure formation from initial density fluctuations. The isotropy of the CMB radiation supports the Big Bang model. Despite tiny fluctuations, the uniformity of the CMB across the sky suggests a common origin for the observable universe. This uniformity is a key prediction of the Big Bang theory. The detection of high-energy particles, such as cosmic rays, provides evidence for processes occurring in the early universe. These particles offer clues about the energetic events that shaped the cosmos. Their study helps to understand the conditions and processes in the early universe. Studies of the large-scale velocity flows of galaxies also support the expanding universe model. These flows show coherent motions over large distances, influenced by the gravitational pull of large structures. They provide further evidence of the universe's dynamic nature. Observations of the cosmic infrared background help to trace the formation and evolution of the first stars and galaxies. This background radiation, originating from the earliest luminous sources, provides insights into the universe's reionization period. It helps to map the timeline of cosmic history. Future observations and missions continue to refine our understanding of the universe. Projects like the James Webb Space Telescope aim to look further back in time, providing even more detailed views of the early universe. These efforts will build on the foundational observational evidence supporting the Big Bang and expanding universe models. Dark energy is one of the most mysterious components of our universe. It is a form of energy that permeates all of space and accelerates the expansion of the universe. Although we cannot see dark energy, its effects are observable on cosmic scales. The discovery of dark energy was made through observations of distant type Ia supernovae. These supernovae indicated that the universe's expansion rate is not slowing down, as previously thought, but is instead accelerating. This unexpected result led to the conclusion that a new form of energy must be driving this acceleration. Dark energy is estimated to make up about 68% of the total energy content of the universe. This dominance means it plays a crucial role in the fate and evolution of the cosmos. Its influence becomes more significant over time as the universe continues to expand. One of the leading theories about dark energy is the cosmological constant, originally proposed by Albert Einstein. This constant represents a uniform energy density that fills space homogeneously. It was initially introduced by Einstein to allow for a static universe, but later discarded after the discovery of cosmic expansion. Another theory suggests that dark energy could be a dynamic field, often referred to as quintessence. Unlike the cosmological constant, quintessence can vary over time and space. Understanding whether dark energy is a constant or dynamic field is a major focus of current research. Dark energy affects the geometry of the universe. Observations of the cosmic microwave background, large-scale structure, and supernovae all suggest a flat universe. This flatness implies a delicate balance between the energy content and the universe's expansion rate. The influence of dark energy is apparent in the large-scale structure of the universe. It affects the growth of cosmic structures by counteracting the gravitational pull of matter. This interaction impacts how galaxies and clusters of galaxies evolve over time. Dark energy also plays a role in the ultimate fate of the universe. If it remains constant, the universe will continue to expand forever, leading to a cold, dark, and empty future known as the Big Freeze. If dark energy increases over time, it could lead to a more dramatic end known as the Big Rip. The nature of dark energy is one of the biggest unsolved problems in cosmology. Understanding it requires precise measurements of the universe's expansion history and the distribution of matter and energy. Upcoming astronomical surveys aim to provide more data to refine our models. The effect of dark energy can be seen in the phenomenon of cosmic acceleration. This acceleration alters the distances to faraway galaxies and affects the light we receive from them. By studying these effects, astronomers can infer properties of dark energy. Gravitational lensing is another tool used to study dark energy. The bending of light from distant objects by massive structures allows astronomers to map the distribution of dark matter and dark energy. These maps provide insights into how dark energy influences the universe's structure. The integrated Sachs-Wolf effect, a subtle imprint on the cosmic microwave background, also offers clues about dark energy. This effect occurs when photons travel through changing gravitational fields influenced by dark energy. Observing this effect helps to understand the impact of dark energy on cosmic scales. High-precision measurements from space missions like the Planck satellite have improved our understanding of dark energy. These measurements provide detailed maps of the cosmic microwave background and insights into the universe's fundamental parameters. Future missions aim to further unravel the mysteries of dark energy. Dark energy has profound implications for theoretical physics. It challenges our understanding of gravity and the fundamental forces of nature. Researchers are exploring new physics beyond the standard model to explain dark energy's properties and behavior. As we continue to investigate dark energy, we deepen our understanding of the universe's most enigmatic force. The answers to questions about dark energy will not only reshape cosmology, but also our broader understanding of physics and the nature of reality. The cosmic microwave background, or CMB, is a crucial piece of evidence for the Big Bang theory. It is the afterglow of the hot, dense state of the early universe, now cooled to microwave frequencies. Discovered in 1965 by Arno Penzias and Robert Wilson, this faint radiation permeates the entire sky. The CMB provides a snapshot of the universe about 380,000 years after the Big Bang, a time known as recombination. Before recombination, the universe was opaque, filled with a hot plasma of electrons and protons. As it cooled, electrons combined with protons to form neutral hydrogen atoms, allowing photons to travel freely. These photons have been traveling through space ever since, stretching to longer wavelengths due to the universe's expansion. This stretching causes the radiation to shift into the microwave region of the electromagnetic spectrum. The temperature of the CMB is now just 2.7 Kelvin, barely above absolute zero. The uniformity of the CMB is remarkable, with temperature variations of only 1 part in 100,000. These tiny fluctuations represent slight density differences in the early universe. They served as the seeds for all the structures we see today, like galaxies and clusters of galaxies. Detailed measurements of the CMB have been made by missions such as COBE, WMAP, and Planck. These missions have mapped the CMB with increasing precision, revealing its detailed structure. The data from these missions have provided critical insights into the universe's composition and evolution. The CMB contains information about the universe's age, geometry, and content. By analyzing its temperature fluctuations, scientists can determine the universe's overall density and the proportions of dark matter, dark energy, and normal matter. This analysis helps refine our understanding of the universe's fundamental parameters. The polarization of the CMB provides additional information about the early universe. Polarization patterns can reveal the influence of gravitational waves from the inflationary period. Detecting these patterns is a major goal of current and future CMB experiments. Now, one of the most striking features of the CMB is the acoustic peaks in its power spectrum. These peaks correspond to sound waves that traveled through the early universe's plasma. Their positions and heights give clues about the universe's geometry and composition. The CMB also shows evidence of the integrated Sachs-Wolfe effect. This effect occurs when CMB photons pass through large-scale structures and are slightly redshifted or blue-shifted. It provides another way to study the influence of dark energy on the universe's evolution. Analyzing the CMB helps test and refine models of cosmic inflation. Inflation predicts specific patterns in the CMB's temperature and polarization fluctuations. Observations that match these predictions strengthen the case for inflation as the correct description of the early universe. The study of the CMB has led to significant discoveries about the universe's history and structure. It has confirmed key aspects of the Big Bang theory and provided evidence for the existence of dark matter and dark energy. These findings have profound implications for cosmology and physics. The future of CMB research involves even more precise measurements and new observational techniques. Upcoming missions aim to map the CMB with greater detail and sensitivity. These efforts will continue to uncover new aspects of the universe's early history and fundamental properties. The CMB is often described as the baby picture of the universe. It provides a direct link to the conditions that prevailed shortly after the Big Bang. Studying this ancient light helps scientists understand the origins and evolution of the cosmos. By examining the CMB, scientists can probe the universe at its largest scales and earliest times. This research not only answers fundamental questions about the universe's birth, but also opens up new questions about its future and the nature of reality. The study of the CMB continues to be a vibrant and dynamic field in modern cosmology. Measuring the rate of expansion of the universe is crucial for understanding its history and future. The Hubble constant, denoted as h0, quantifies this rate. It represents the velocity at which galaxies recede from us per unit distance. There are several methods to measure the Hubble constant. One approach is to use standard candles, such as Cepheid variables and type Ia supernovae. These objects have known luminosities, allowing astronomers to calculate distances by comparing their intrinsic brightness to their observed brightness. Cepheid variables are pulsating stars with a well-established relationship between their pulsation period and luminosity. By measuring the period of these stars in distant galaxies, astronomers can determine their distances. This method helps calibrate other distance measurement techniques. Type Ia supernovae are stellar explosions with a consistent peak luminosity. Observing these supernovae in distant galaxies provides accurate distance measurements. Combining these distances with redshift data allows for precise calculations of the Hubble constant. Another method involves using the cosmic microwave background, CMB. The CMB provides a snapshot of the universe at the time of recombination, about 380,000 years after the Big Bang. By analyzing the temperature fluctuations in the CMB, scientists can infer the universe's rate of expansion. Baryon acoustic oscillations, BAOs, are another tool for measuring cosmic distances. BAOs are regular, periodic fluctuations in the density of visible matter caused by sound waves in the early universe. These oscillations provide a standard ruler for measuring large-scale distances. The combination of CMB data and BAO measurements offers a powerful way to determine the Hubble constant. This approach leverages the early universe's well-understood physics to infer the expansion rate. It complements distance measurements from standard candles. Gravitational lensing provides an additional method for measuring the Hubble constant. When light from a distant galaxy is bent by a massive foreground object, it creates multiple images of the background galaxy. Analyzing the time delays between these images can yield the Hubble constant. Quasars, extremely bright and distant objects, also serve as tools for measuring cosmic expansion. By observing the time delays in the light variations from lensed quasars, astronomers can infer distances and the Hubble constant. This method relies on precise monitoring of quasar brightness changes. Another innovative approach is using the Sunyaev-Zeldovich effect, which involves observing the distortion of the CMB by hot gas in galaxy clusters. This effect provides independent distance measurements, contributing to the determination of the Hubble constant. The Tully-Fisher relation is a correlation between the luminosity of spiral galaxies and their rotational velocities. By measuring the rotational speed of a galaxy, astronomers can estimate its luminosity and distance. This relation helps refine distance scales used to measure the Hubble constant. The rate of expansion can also be studied using redshift surveys of galaxies. These surveys map the distribution of galaxies in 3 dimensions, revealing patterns and structures influenced by cosmic expansion. They provide crucial data for calculating the Hubble constant. Recent observations have led to some tension between different measurements of the Hubble constant. Measurements from the CMB and large-scale structure suggest a lower value, while those from supernovae and Cepheids suggest a higher value. This discrepancy has sparked active research and debate. Understanding this tension may reveal new physics beyond the current cosmological models. It could point to unknown aspects of dark energy, dark matter, or the nature of gravity. Resolving the discrepancy is a major goal in cosmology. Future missions and observations aim to provide more precise measurements of the Hubble constant. Improved technology and new observational techniques will refine our understanding of the universe's expansion. These efforts will continue to enhance our knowledge of cosmic history and the fundamental properties of the universe. Light years and parsecs are both units of distance used in astronomy to measure vast separations in space. A light year is the distance that light travels in 1 year, roughly 5.88 trillion miles, or 9.46 trillion kilometers. This unit is helpful for expressing the immense distances between stars and galaxies. A parsec, short for parallax second, is another unit of distance commonly used by astronomers. 1 parsec is approximately 3.26 light-years. It is based on the apparent shift in position of a nearby star against the background of distant stars, as observed from Earth at opposite ends of its orbit. The concept of a light-year helps illustrate the vastness of space. For instance, Proxima Centauri, the nearest star to the Sun, is about 4.24 light-years away. This means that light from Proxima Centauri takes over 4 years to reach us. Parsecs are particularly useful when measuring distances within our galaxy and to nearby galaxies. The Andromeda Galaxy, for example, is about 780 kiloparsecs from the Milky Way. Using parsecs simplifies these large numbers, making them more manageable for astronomers. Light years are often used in discussions about the age of light we observe. When we look at a star 10 light years away, we are seeing it as it was 10 years ago. This concept allows astronomers to study the history and evolution of distant objects. Parsecs are derived from the method of stellar parallax. This method involves measuring the angle of apparent movement of a star relative to distant background stars as Earth orbits the Sun. A star with a parallax angle of 1 arcsecond is defined to be 1 parsec away. The choice between light years and parsecs depends on the context. Light years are more intuitive for the general public and educational purposes, while parsecs are more precise for scientific calculations. Both units help convey the incredible scales involved in astronomy. Distances to the farthest objects in the universe are often expressed in gigaparsecs. 1 gigaparsec is 1 billion parsecs. This unit is useful for discussing the scale of the observable universe, which spans several gigaparsecs. The unit of a light year connects to the speed of light, a fundamental constant in physics. It underscores the finite speed at which information and matter can travel. This relationship is key to understanding the structure and behavior of the universe. Parsecs are directly related to observational techniques in astronomy. Measuring the parallax shift of stars provides a fundamental rung on the cosmic distance ladder. This ladder allows astronomers to measure distances to progressively farther objects. Both light years and parsecs reflect the challenges of measuring astronomical distances. These units emerged from the need to describe the vast separations between celestial objects accurately and efficiently. They are integral to the field of astrophysics. The distinction between these units highlights the development of astronomical measurement techniques. From early observations of stellar parallax to modern methods involving precise instruments, our ability to measure cosmic distances has advanced significantly. Understanding these units enhances our appreciation of the universe's scale. Whether considering the distance to a nearby star or a distant galaxy, Light years and parsecs provide a framework for comprehending these vast expanses. They bridge the gap between human experience and the enormity of space. Both units also play a role in various astronomical phenomena. For example, understanding the distances involved helps in calculating the intrinsic brightness of stars and galaxies. This information is crucial for studying their properties and evolution. In summary, light years and parsecs are essential tools for measuring and describing the universe. They allow astronomers to communicate distances with precision and clarity. As our exploration of the cosmos continues, these units will remain fundamental to our understanding of the universe. Standard candles are crucial tools in astronomy for measuring cosmic distances. They are objects with known luminosities, allowing astronomers to determine their distances by comparing their intrinsic brightness to their observed brightness. Two of the most important standard candles are Cepheid variables and Type Ia supernovae. Cepheid variables are pulsating stars with a direct relationship between their pulsation period and luminosity. By measuring the period of a Cepheid's brightness variations, astronomers can determine its absolute magnitude. This makes Cepheids reliable distance indicators for relatively nearby galaxies. The discovery of the period-luminosity relationship in Cepheid variables was made by Henrietta Swan Leavitt in the early 20th century. Her work provided a powerful tool for measuring the scale of the universe. Cepheids have since been used to establish distances to many nearby galaxies. Type Ia supernovae are stellar explosions that occur in binary systems where one of the stars is a white dwarf. When the white dwarf accumulates enough material from its companion star, it reaches a critical mass and explodes. These supernovae have a consistent peak luminosity, making them excellent standard candles for more distant galaxies. The uniform brightness of Type Ia supernovae allows astronomers to measure distances across vast stretches of the universe. By comparing the observed brightness of these supernovae to their known luminosity, distances to their host galaxies can be calculated. This method has been pivotal in studying the expansion of the universe. Standard candles help calibrate other distance measurement techniques, forming the foundation of the cosmic distance ladder. Cepheids are used to measure distances within our galaxy and to nearby galaxies. Type Ia supernovae extend this reach to much greater distances, helping map the universe's expansion history. The use of standard candles has led to significant discoveries in cosmology. Observations of Type Ia supernovae in distant galaxies revealed the accelerated expansion of the universe. This discovery provided key evidence for the existence of dark energy. Cepheid variables have also been instrumental in refining the Hubble constant. By providing accurate distance measurements to nearby galaxies, they help calibrate the relationship between redshift and distance. This calibration is essential for determining the rate of the universe's expansion. The study of standard candles continues to evolve with advances in technology and observational techniques. Improved telescopes and instruments allow for more precise measurements of Cepheid variables and Type Ia supernovae. These improvements enhance our understanding of cosmic distances and the universe's structure. Standard candles also play a role in understanding the local universe. They help determine the distances to nearby galaxies, providing a clearer picture of our cosmic neighborhood. This information is crucial for studying galaxy formation and evolution. The reliability of standard candles depends on accurately determining their intrinsic luminosities. For Cepheid variables, this involves precise measurements of their pulsation periods and apparent magnitudes. For Type Ia supernovae, understanding the physics of their explosions ensures consistent luminosity estimates. Both Cepheids and Type Ia supernovae have been observed in various environments, from spiral galaxies to dwarf galaxies. These observations confirm the universality of their properties, reinforcing their status as standard candles. This universality is key to their effectiveness in measuring distances. Standard candles are also used to study the interstellar medium. Observations of Cepheids and supernovae can reveal the presence of interstellar dust, which affects the observed brightness of these objects. Understanding this dust helps refine distance measurements. The future of standard candle research includes the search for even more reliable distance indicators. New types of standard candles, such as certain types of variable stars or other supernovae, may provide additional tools for measuring cosmic distances. These discoveries will further enhance our ability to map the universe. In summary, standard candles like Cepheid variables and Type Ia supernovae are indispensable for measuring cosmic distances. They provide the foundation for the cosmic distance ladder, helping to unravel the structure and expansion of the universe. As observational techniques improve, these standard candles will continue to illuminate our understanding of the cosmos. Redshift is a phenomenon where the wavelength of light from an object is stretched, making it appear redder as it moves away from us. This effect is observed in the light from distant galaxies and is a key indicator of the expanding universe. The greater the redshift, the faster the galaxy is receding from us. Hubble's constant, denoted as H0, quantifies the rate of this expansion. It defines the relationship between the distance of a galaxy and its recessional velocity due to the expansion of the universe. Essentially, it tells us how fast the universe is expanding at different distances. The concept of redshift is crucial for understanding cosmic distances and the universe's expansion history. By measuring the redshift of galaxies, astronomers can determine their velocities relative to Earth. This information, combined with distance measurements, helps calculate Hubble's constant. Edwin Hubble's observations in the 1920s established the linear relationship between a galaxy's distance and its recessional velocity, leading to the formulation of Hubble's law. This law provides a foundation for modern cosmology, linking redshift and distance through Hubble's constant. Hubble's law can be expressed as V H0d, where V is the galaxy's recessional velocity, H0 is Hubble's constant, and d is the distance to the galaxy. This equation shows that the farther away a galaxy is, the faster it appears to be moving away from us. Measuring redshift involves observing the spectral lines of elements in a galaxy's light. These lines shift towards the red end of the spectrum as the galaxy recedes. By comparing the shifted lines to their known wavelengths, astronomers can calculate the redshift and, consequently, the galaxy's velocity. Determining Hubble's constant has been a central goal in cosmology. Different methods, including observations of Cepheid variables and Type Ia supernovae, have provided estimates of H0. However, there is still some tension between values obtained from different techniques. The Hubble tension refers to the discrepancy between the Hubble constant values derived from the early universe observations, like the cosmic microwave background, and those obtained from local measurements, such as supernovae and Cepheids. Resolving this tension is a major focus of current research. Redshift surveys map the distribution of galaxies and their velocities across the universe. These surveys provide data that helps refine the value of Hubble's constant and improve our understanding of large-scale cosmic structures. They are essential for studying the universe's expansion history. Quasars, extremely luminous and distant objects, also help measure redshift and study the expansion of the universe. Their high brightness makes them visible across vast distances, providing valuable data for calculating redshift and exploring the early universe. The relationship between redshift and distance supports the Big Bang theory. As we look further into space, we see galaxies at earlier stages of their development. This observational evidence confirms that the universe has been expanding from a hot, dense state. Hubble's constant is not truly constant over time. It changes as the universe evolves. However, it provides a snapshot of the current expansion rate. Understanding how H0 varies with time helps cosmologists trace the history of cosmic expansion and predict the universe's future behavior. Gravitational lensing, where the light from distant objects is bent by massive foreground structures, can also provide insights into redshift and Hubble's constant. Analyzing the lensing effect allows astronomers to measure distances and refine estimates of cosmic expansion. Advanced telescopes and space missions continue to improve redshift measurements. Instruments like the James Webb Space Telescope will provide more precise data, helping to resolve the Hubble tension and refine our understanding of the universe's expansion. In summary, redshift and Hubble's constant are fundamental concepts in cosmology. They describe the expanding universe and help measure cosmic distances. Continued research and advanced observations aim to refine these measurements, enhancing our understanding of the universe's past, present, and future. The parallax method is a fundamental technique for measuring the distances to nearby stars. It relies on the apparent shift in a star's position as observed from Earth at different points in its orbit around the Sun. This shift, or parallax angle, is small but measurable. By observing a star's position at two different times of the year, separated by 6 months, astronomers can calculate the parallax angle. This angle is then used to determine the distance to the star using simple trigonometry. The smaller the parallax angle, the farther away the star is. The parallax method is most effective for stars within a few hundred light-years of Earth. Beyond this range, the parallax angles become too small to measure accurately with current technology. However, it remains one of the most direct and reliable methods for measuring stellar distances. 1 arcsecond of parallax corresponds to a distance of 1 parsec, or about 3.26 light-years. This relationship is the basis for the parsec as a unit of astronomical distance. Measuring the parallax angles of stars is essential for calibrating other distance measurement techniques. The European Space Agency's Hipparcos satellite, launched in 1989, revolutionized astrometry by measuring the parallaxes of over 100,000 stars with unprecedented precision. Hipparcos data significantly improved our understanding of stellar distances and the structure of our galaxy. Following Hipparcos, the Gaia mission, launched in 2013, has taken astrometry to new heights. Gaia is mapping the positions and parallaxes of over 1 billion stars, providing detailed three-dimensional maps of the Milky Way. This wealth of data enhances our knowledge of stellar motions and distances. The parallax method also helps in determining the intrinsic brightness of stars. By knowing the exact distance to a star, astronomers can calculate its absolute magnitude. This information is crucial for studying the properties and life cycles of stars. Measuring stellar parallaxes contributes to our understanding of the scale of the universe. Accurate distances to nearby stars serve as the first rung on the cosmic distance ladder. This foundational step is essential for measuring distances to more distant objects using other methods. The precision of parallax measurements has improved dramatically with advancements in technology. Modern telescopes and space missions provide increasingly accurate data, allowing astronomers to measure parallax angles with greater precision. These improvements have expanded the range of stars for which we can determine distances. Parallax data is also valuable for studying stellar populations and their distributions within the Milky Way. By mapping the positions and distances of stars, astronomers can trace the structure and formation history of our galaxy. This information helps to unravel the complex processes that shape galaxies. The parallax method is not limited to stars within our galaxy. It can also be applied to nearby star clusters and other stellar systems. Accurate distance measurements to these objects help calibrate other distance indicators and refine our models of galactic and extragalactic structures. Astrometry, the precise measurement of stellar positions and motions, relies heavily on parallax data. This field of study provides insights into the dynamics of stars and the gravitational forces acting on them. Understanding these dynamics is crucial for studying the evolution of the Milky Way and other galaxies. Parallax measurements are fundamental to many areas of astrophysics. They provide the baseline for determining the scale of the universe and calibrating other distance measurement techniques. This foundational role makes the parallax method a cornerstone of modern astronomy. Future missions and technological advancements will continue to improve the precision of parallax measurements. As our ability to measure smaller and more distant parallaxes increases, we will gain deeper insights into the structure and scale of the universe. These advancements will further refine our understanding of cosmic distances and the nature of the cosmos. In summary, the parallax method is a vital tool for measuring stellar distances. It provides the first step on the cosmic distance ladder and calibrates other distance measurement techniques. As technology advances, parallax measurements will continue to play a crucial role in expanding our understanding of the universe. The cosmic distance ladder is a series of methods by which astronomers determine the distances to celestial objects. Each rung of the ladder uses a different technique that builds on the previous one, extending our reach further into space. The process starts with the most direct measurements and progresses to more complex methods. The first rung on the cosmic distance ladder is the parallax method. This technique measures the apparent shift in a star's position as observed from Earth at different times of the year. Parallax is most effective for stars within a few hundred light-years. Beyond the reach of parallax, Astronomers use standard candles, such as Cepheid variables. These stars have a known relationship between their pulsation periods and intrinsic brightness. By measuring their periods and apparent brightness, astronomers can determine their distances. Type Ia supernovae serve as another standard candle for measuring distances to galaxies far beyond the Milky Way. These supernovae have a consistent peak luminosity, allowing astronomers to calculate their distances by comparing observed brightness to known luminosity. This method extends the distance scale significantly. Moving further up the ladder, astronomers use the Tully-Fisher relation. This relationship links the rotational speed of spiral galaxies to their luminosity. By measuring the rotational speed, the intrinsic brightness can be determined, providing another way to estimate distances to galaxies. The Faber-Jackson relation is similar but applies to elliptical galaxies. It correlates the velocity dispersion of stars within these galaxies to their luminosity. This relationship helps measure distances to elliptical galaxies, complementing methods used for spiral galaxies. Surface brightness fluctuations provide another rung on the ladder. This method analyzes variations in the brightness of a galaxy's light distribution. These fluctuations are used to estimate distances, particularly for galaxies within clusters. Gravitational lensing, where light from a distant object is bent by a massive foreground object, offers a way to measure distances based on lensing effects. Time delays between multiple images of the same source can provide distance estimates, especially for very distant galaxies and quasars. Baryon acoustic oscillations, BAOs, serve as a standard ruler in the universe. These regular periodic fluctuations in the density of visible matter provide a scale for measuring large-scale distances. BAOs offer a powerful tool for understanding the expansion history of the universe. The tip of the red giant branch, TRGB, is another method used for distance measurement. The TRGB method involves identifying the brightest red giants in a galaxy. Their consistent luminosity serves as a reliable distance indicator for nearby galaxies. Using galaxy redshift surveys, astronomers can map the distribution of galaxies and their velocities. This mapping provides data on the large-scale structure of the universe and helps refine distance measurements. It plays a crucial role in understanding cosmic expansion. Quasars, with their immense brightness, are visible across vast distances and help extend the cosmic distance ladder. Observing the redshift of quasars allows astronomers to probe the universe's early history and measure distances to the farthest reaches of space. The cosmic microwave background, CMB, provides a key reference point for the distance ladder. Analyzing the CMB's fluctuations helps determine the universe's scale and expansion rate. It connects the entire distance ladder to the universe's earliest moments. Gamma-ray bursts, some of the brightest explosions in the universe, are also used as distance indicators. Their luminosity and the afterglow provide information on distances to their host galaxies, helping to extend our reach further into the cosmos. The cosmic distance ladder is essential for calibrating and verifying distance measurement methods. Each rung provides a stepping stone to the next, creating a comprehensive framework for understanding the universe's scale and structure. This interconnected system of measurements allows astronomers to map the cosmos with increasing precision. As technology advances and new methods are developed, the cosmic distance ladder will continue to be refined. Future observations and missions will enhance our ability to measure distances accurately, further expanding our understanding of the universe's vastness and complexity. The observable universe refers to the portion of the entire universe that we can see or detect from Earth. Its size is determined by the age of the universe and the speed of light. Given the universe's age of approximately 13.8 billion years, the observable universe has a radius of about 46.5 billion light-years. The term observable is crucial because it denotes the limits of our ability to detect light or other signals. Beyond this limit, light from distant objects has not had enough time to reach us since the Big Bang. Thus, the observable universe is not the entire universe, but just a fraction we can currently observe. The size of the observable universe encompasses everything from the smallest particles to the largest cosmic structures. It includes galaxies, stars, planets, dark matter, and dark energy. This vast expanse is filled with billions of galaxies, each containing billions of stars. Measuring the size of the observable universe involves understanding cosmic expansion. As the universe expands, distant galaxies move away from us, making the observable universe larger than just 13.8 billion light-years. The expansion rate affects our calculations of the universe's size. Light from the most distant objects we can observe, such as quasars and the cosmic microwave background, provides clues about the size and structure of the observable universe. These observations help scientists refine their measurements and models of cosmic expansion. The observable universe also includes regions that are currently beyond our detection capabilities. Future technologies and observations may extend our view, revealing even more of the universe. Each new discovery pushes the boundaries of the observable universe further. Despite its vastness, the observable universe is finite. This finiteness is due to the finite speed of light and the age of the universe. Understanding these limits helps scientists explore the nature of the universe beyond what we can currently see. The concept of the observable universe raises questions about what lies beyond its boundaries. The unobservable universe could be much larger, potentially infinite. This idea challenges our understanding of cosmology and the limits of human observation. The structure within the observable universe is highly organized. Galaxies form clusters and superclusters, interconnected by vast cosmic filaments. These structures create a web-like pattern that extends across the observable universe, shaped by gravity and cosmic expansion. Dark matter and dark energy play significant roles in defining the observable universe's structure and size. Dark matter's gravitational effects influence the formation of galaxies and large-scale structures. Dark energy drives the accelerated expansion of the universe, affecting its size over time. The observable universe is also a time capsule, showing us the universe's history. Light from distant galaxies takes billions of years to reach us, so observing them reveals what they looked like in the past. This allows scientists to study the universe's evolution over cosmic time. Cosmic inflation, a period of rapid expansion shortly after the Big Bang, has a significant impact on the observable universe's size. Inflation stretched the universe, making the observable region much larger than it would have been otherwise. This theory helps explain the uniformity and structure of the observable universe. Understanding the observable universe's size helps in calculating the density and composition of the cosmos. Observations suggest that the universe is composed of about 68% dark energy, 27% dark matter, and 5% normal matter. These proportions influence the universe's expansion and evolution. The observable universe's limits are constantly being tested and refined through observations and theoretical models. Advances in telescope technology and cosmic surveys continue to push the boundaries of what we can observe. These efforts enhance our understanding of the universe's size and structure. In summary, the observable universe is a vast and complex expanse defined by the age of the universe and the speed of light. It encompasses everything we can detect and provides a window into the past and the nature of the cosmos. As technology and observations advance, our understanding of the observable universe will continue to grow, revealing new insights into the nature of the universe itself. The observable limits of the universe define the boundaries of what we can see and measure. These limits are determined by the age of the universe and the speed of light, restricting our view to objects whose light has had time to reach us since the Big Bang. Anything beyond these limits remains invisible to us. As the universe expands, these observable limits extend further. This means we are continually seeing light from increasingly distant regions, providing new insights into the early universe. However, there is still a finite boundary to what we can observe. The concept of a light horizon is essential in understanding these limits. This horizon marks the maximum distance from which light can travel to us within the age of the universe. Beyond this horizon, objects exist, but their light has not had enough time to reach us. Cosmic inflation, an early rapid expansion of the universe, has a significant impact on the observable limits. Inflation stretched the universe beyond what we could otherwise see, pushing the light horizon further out. This expansion allows us to observe a more extensive portion of the universe than we might expect. The cosmic microwave background radiation is a critical marker of the observable universe's limits. It represents the farthest point we can see, dating back to the recombination era, when the universe first became transparent to light. Beyond this, The universe was opaque, and we cannot observe directly. Observing the cosmic microwave background provides a snapshot of the universe at about 380,000 years old. This radiation is uniform in all directions, indicating that the observable universe is isotropic and homogeneous on large scales. These observations help define the limits of our cosmic view. Another limit is set by the finite speed of light, which means we see distant objects as they were in the past. The farther away we look, the older the light we observe. This time delay effect allows us to study the history of the universe, but also constrains the current view of distant objects. The observable universe's limits also depend on our detection capabilities. Advances in telescope technology and observation methods continually push these limits outward. Each improvement allows us to see fainter and more distant objects, expanding our view of the cosmos. Dark energy, driving the accelerated expansion of the universe, affects the observable limits as well. This expansion can stretch the distance to the farthest observable objects, potentially moving some out of our reach over time. Understanding dark energy is crucial for predicting how our observable limits might change. The concept of the particle horizon is another way to think about observable limits. The particle horizon marks the boundary beyond which particles could not have traveled to us since the Big Bang. It defines the ultimate edge of what we can observe in terms of particle interactions. Gravitational waves provide a different perspective on observable limits. These ripples in space-time travel at the speed of light and can pass through matter without significant absorption or scattering. Observing gravitational waves from distant events offers a new way to study the universe's limits. The observable limits also influence our understanding of the universe's large-scale structure. Mapping galaxies and other cosmic structures within these limits helps us understand the distribution and evolution of matter. These maps are essential for studying cosmic formation and growth. Future missions aim to explore beyond current observable limits. Projects like the James Webb Space Telescope will look further back in time and deeper into space than ever before. These missions will push the boundaries of what we can observe, revealing new aspects of the universe. Theoretical models suggest that the universe beyond our observable limits could be vastly different. While we see a relatively uniform cosmos, regions beyond our reach might have different properties or conditions. These possibilities challenge our understanding and drive further exploration. In summary, the observable limits of the universe define the boundaries of what we can currently see and measure. These limits are shaped by the age of the universe, the speed of light, and our observational capabilities. As technology advances, we continue to push these boundaries, expanding our understanding of the cosmos. The structure of the observable universe is a vast and intricate web of galaxies, clusters, and superclusters. These structures are connected by long filaments of dark matter and separated by immense voids. This large-scale structure is often referred to as the cosmic web. Galaxies are the fundamental building blocks of the universe's structure. They range from small dwarf galaxies with millions of stars to giant ellipticals containing trillions. Galaxies are grouped into clusters which are bound together by gravity. Clusters of galaxies are among the largest structures in the universe. They can contain thousands of galaxies, along with hot gas and dark matter. These clusters are connected by even larger formations known as superclusters. Superclusters are vast collections of galaxy clusters. They form massive structures that can span hundreds of millions of light-years. Our own Milky Way galaxy is part of the local group, which belongs to the Virgo supercluster. The cosmic web is the large-scale structure that connects these galaxies and clusters. It consists of filaments, sheets, and nodes formed by dark matter and baryonic matter. These structures create a web-like pattern across the universe. Dark matter plays a crucial role in shaping the cosmic web. It provides the gravitational framework for the formation of galaxies and clusters. Although dark matter is invisible, its presence is inferred from its gravitational effects on visible matter. Observations of the cosmic microwave background provide evidence for the initial density fluctuations that grew into the large-scale structures we see today. These fluctuations served as seeds for the formation of galaxies and clusters through gravitational collapse. Voids are vast, empty regions between the filaments and clusters. They contain very few galaxies compared to the denser regions. These voids help define the large-scale structure by providing contrast to the denser filaments and clusters. The distribution of galaxies in the observable universe is not random. Galaxies are found along the filaments of the cosmic web, often in clusters or groups. This pattern reflects the underlying distribution of dark matter and the processes of galaxy formation. Redshift surveys have mapped the distribution of galaxies across large volumes of the universe. These surveys reveal the intricate structure of the cosmic web and provide data for studying the universe's expansion and evolution. They are essential tools for cosmology. Galaxy mergers and interactions play a significant role in the evolution of the universe's structure. These events can trigger star formation, change galaxy shapes, and redistribute matter. The results of these interactions are visible in the diverse forms of galaxies we observe. Gravitational lensing, the bending of light by massive objects, allows astronomers to map the distribution of dark matter. This technique provides a way to study the structure of the universe on various scales, from individual clusters to the entire cosmic web. The large-scale structure of the universe is influenced by dark energy, which drives the accelerated expansion. This expansion affects the growth and distribution of galaxies and clusters. Understanding dark energy is crucial for studying the evolution of the cosmic web. Computer simulations have been instrumental in modeling the formation and evolution of the universe's structure. These simulations use the laws of physics to recreate the development of galaxies and clusters over billions of years. They provide insights into the processes shaping the cosmic web. The study of the universe's structure continues to advance with new observations and technologies. Future surveys and missions will provide more detailed maps of the cosmos, revealing finer details of the cosmic web. These efforts will enhance our understanding of the universe's formation and evolution. Telescopes and satellites are essential tools for observing the universe. They allow astronomers to see objects that are far beyond the reach of the naked eye. These instruments collect and magnify light from distant celestial bodies, providing detailed images and spectra. Optical telescopes are the most common type, using lenses or mirrors to gather and focus visible light. Ground-based optical telescopes, like those at observatories, capture stunning images of stars, galaxies, and nebulae. The Hubble Space Telescope is a notable example that operates above Earth's atmosphere, providing clear and detailed views of the cosmos. Radio telescopes detect radio waves emitted by celestial objects. These telescopes can observe phenomena that are invisible in visible light, such as pulsars, quasars, and cosmic microwave background radiation. Arrays of radio telescopes, like the Very Large Array, combine signals to create high-resolution images. Infrared telescopes observe heat radiation from celestial objects. They can see through dust clouds that obscure visible light, revealing hidden structures in star-forming regions and the centers of galaxies. The Spitzer Space Telescope and the upcoming James Webb Space Telescope specialize in infrared observations. X-ray telescopes detect high-energy X-rays from sources like black holes, neutron stars, and supernova remnants. These telescopes, such as the Chandra X-ray Observatory, provide insights into the most energetic processes in the universe. They are crucial for studying the environments around extreme objects. Ultraviolet telescopes observe light in the ultraviolet spectrum, which is mostly absorbed by Earth's atmosphere. Space-based ultraviolet telescopes like the Hubble Space Telescope study young stars, hot gas in galaxies, and the interstellar medium. These observations help understand the life cycles of stars and galaxies. Gamma-ray telescopes detect the highest energy photons in the universe. These telescopes, including the Fermi Gamma-ray Space Telescope, observe gamma-ray bursts, active galactic nuclei, and other extreme phenomena. Gamma-ray observations provide insights into the most violent events in the cosmos. Space telescopes have the advantage of being above Earth's atmosphere, which can distort and absorb light. This position allows them to observe a broader range of wavelengths with greater clarity. Space missions like Hubble, Chandra, and James Webb have revolutionized our understanding of the universe. Ground-based observatories are continually improving with advanced technologies. Adaptive optics correct for atmospheric distortion, providing clearer images. Large telescopes, like the extremely large telescope under construction, will offer unprecedented views of the universe from the ground. Interferometry combines signals from multiple telescopes to simulate a much larger instrument. This technique is used in both radio and optical astronomy to achieve higher resolution images. Projects like the Event Horizon Telescope use interferometry to capture detailed images of black holes. Spectroscopy is a vital tool for understanding the composition and properties of celestial objects. By analyzing the light spectrum, astronomers can determine the chemical makeup, temperature, density, and motion of stars and galaxies. Spectroscopic instruments are integral to both ground-based and space telescopes. Space missions are also essential for planetary exploration. Probes and rovers, like those sent to Mars and the outer planets, provide detailed information about our solar system. These missions complement telescopic observations by offering direct measurements and close-up images. New technologies continue to expand our observational capabilities. Advances in detector sensitivity, computational power, and data analysis methods are pushing the boundaries of what we can observe. Future telescopes and missions will explore the universe in even greater detail. International collaborations enhance our ability to observe the universe. Large projects often involve multiple countries and organizations, pooling resources and expertise. These collaborations enable the construction and operation of sophisticated telescopes and space missions. As we develop more advanced tools for observing the universe, we continue to uncover new phenomena and deepen our understanding of cosmic processes. Each new observation brings us closer to answering fundamental questions about the nature and origin of the universe. Important observations and discoveries have significantly shaped our understanding of the universe. One of the most profound was Edwin Hubble's discovery of the expanding universe. By observing the redshift of galaxies, he showed that they are moving away from us, leading to the formulation of Hubble's law. The detection of the cosmic microwave background radiation was a groundbreaking discovery. This faint glow, observed by Arno Penzias and Robert Wilson, provided strong evidence for the Big Bang theory. It represents the afterglow of the early universe, offering a snapshot of the cosmos shortly after its formation. The discovery of dark matter emerged from observations of galaxy rotation curves. Astronomers noticed that the outer regions of galaxies rotate faster than expected based on visible matter alone. This discrepancy suggested the presence of unseen mass, now known as dark matter. Observations of Type Ia supernovae revealed the accelerating expansion of the universe. These standard candles indicated that distant galaxies are receding faster than previously thought. This discovery led to the concept of dark energy, a mysterious force driving the acceleration. The mapping of the large-scale structure of the universe has been a significant achievement. Surveys like the Sloan Digital Sky Survey have charted the distribution of galaxies, revealing a cosmic web of filaments, clusters, and voids. These maps provide insights into the universe's formation and evolution. The observation of gravitational waves opened a new window into the universe. Detected by LIGO, these ripples in space-time confirmed a key prediction of Einstein's general theory of relativity. Gravitational waves allow us to observe cosmic events, such as black hole mergers, in a completely new way. The detailed study of the cosmic microwave background by the Planck satellite has provided precise measurements of the universe's age, composition, and geometry. This data has refined our understanding of the Big Bang and the subsequent evolution of the cosmos. Discoveries of exoplanets have revolutionized our understanding of planetary systems. Observations by telescopes like Kepler have identified thousands of planets orbiting other stars. These discoveries suggest that planets are common in the universe and have implications for the search for life beyond Earth. The detection of quasars revealed the existence of supermassive black holes at the centers of galaxies. These extremely luminous objects are powered by the accretion of matter onto black holes. Quasars serve as beacons illuminating the early universe and the growth of cosmic structures. The discovery of cosmic inflation provided a framework for understanding the rapid expansion of the universe immediately after the Big Bang. This theory explains the uniformity of the cosmic microwave background and the large-scale structure of the universe. Inflationary models continue to be a vital area of research. Observations of the Higgs boson at the Large Hadron Collider confirmed the existence of the particle responsible for giving other particles mass. This discovery was a major milestone in particle physics and validated the Standard Model. It has profound implications for our understanding of fundamental forces and particles. Gamma-ray bursts, the most energetic explosions in the universe, were first observed by satellite missions. These bursts provide insights into the deaths of massive stars and the formation of black holes. Studying gamma-ray bursts helps astronomers understand extreme physical processes. The identification of the first interstellar object, Oumuamua, passing through our solar system, was a remarkable discovery. This observation provided a unique opportunity to study an object from another star system. It raised intriguing questions about the nature and origin of such interstellar visitors. The detection of neutrinos from distant cosmic sources has added a new dimension to our understanding of high-energy astrophysical processes. Observatories like IceCube detect these elusive particles, offering insights into supernova, black holes, and other extreme phenomena. Continued observations and discoveries drive the progress of astronomy and cosmology. Each new finding builds on previous knowledge, expanding our understanding of the universe. As technology and observational techniques advance, we can expect even more groundbreaking discoveries in the future. The cosmic horizon represents the maximum distance from which light has had time to reach us since the beginning of the universe. It marks the boundary beyond which we cannot observe or receive information. This horizon is determined by the age of the universe and the speed of light. Beyond the cosmic horizon, there are regions of the universe that remain inaccessible to us. The light from these distant regions has not had enough time to travel across the expanding cosmos to reach Earth. As the universe continues to age, the cosmic horizon gradually extends further. The concept of the cosmic horizon is tied to the finite speed of light. Even though the universe may be infinitely large, we are limited by how far light has traveled since the Big Bang. This creates a visible bubble around us, defining the observable universe. The current estimate for the radius of the cosmic horizon is about 46.5 billion light-years. This means we can observe objects within this radius, but anything beyond remains out of reach. The expansion of the universe plays a crucial role in shaping this horizon. Inflation, a rapid expansion phase in the early universe, has significantly influenced the cosmic horizon. It stretched the universe to such an extent that regions once close together were pushed far apart. This inflationary period set the stage for the observable limits we see today. The cosmic horizon is sometimes confused with the event horizon of a black hole. However, while a black hole's event horizon is a point of no return for matter and light, the cosmic horizon simply marks the farthest distances we can observe. It's a boundary defined by time and light travel, rather than gravity. As we look back in time, observing distant galaxies, we are effectively looking towards the cosmic horizon. These distant observations provide insights into the early universe, helping us understand its evolution and structure. Each observation brings us closer to the edge of the observable universe. The cosmic horizon is not static. It evolves over time. As the universe ages, light from more distant regions will have time to reach us, gradually expanding the observable universe. This dynamic nature reflects the ongoing process of cosmic expansion. Understanding the cosmic horizon helps astronomers refine their models of the universe. It provides a framework for studying the limits of our observational capabilities. This understanding is essential for interpreting data from deep space observations and cosmic background radiation. The concept of the cosmic horizon also raises philosophical questions about the nature of the universe beyond what we can observe. If the universe is infinitely large, there could be countless regions beyond our horizon, each with its own structures and phenomena. This idea challenges our perception of the universe's scale. The cosmic horizon's significance extends to the study of dark energy. Dark energy affects the rate of expansion, which in turn influences the size of the observable universe. Understanding this relationship is key to unraveling the mysteries of dark energy and cosmic acceleration. Cosmic microwave background radiation provides a view close to the cosmic horizon. This radiation, a relic from the early universe, offers a snapshot of the cosmos at a young age. Studying this background helps define the characteristics and limits of the observable universe. Future observations and missions aim to push the boundaries of the cosmic horizon even further. Advanced telescopes and space probes will seek to observe the earliest galaxies and cosmic phenomena. These efforts will expand our understanding of the universe's farthest reaches. As technology advances, our ability to study the cosmic horizon improves. Each new discovery and observation brings us closer to understanding the full scope of the universe. The cosmic horizon remains a frontier, continuously challenging our knowledge and inspiring exploration. In summary, the cosmic horizon defines the observable limits of the universe, shaped by the age of the universe and the speed of light. It represents the edge of what we can see and measure, continually expanding as the universe evolves. Understanding this horizon is crucial for exploring the vastness of the cosmos. The event horizon and the particle horizon are two different concepts in cosmology. The event horizon refers to a boundary in space-time beyond which events cannot affect an observer. It is commonly associated with black holes, marking the point where the escape velocity exceeds the speed of light. In contrast, the particle horizon is the maximum distance from which particles could have traveled to the observer in the age of the universe. It defines the boundary of the observable universe, determined by the time elapsed since the Big Bang and the speed of light. The event horizon of a black hole is a region beyond which nothing, not even light, can escape. This boundary is crucial for understanding the behavior of black holes and the fate of objects that fall into them. It represents a point of no return. The particle horizon, on the other hand, is concerned with the observable limits of the universe. It is the edge of the observable universe, beyond which we cannot see or receive information because the light has not had enough time to reach us. While the event horizon is a fixed boundary around a black hole, the particle horizon expands over time as the universe ages. This expansion occurs because light from more distant regions has had more time to travel and reach us. Both horizons are influenced by the speed of light, but in different ways. The event horizon is defined by the escape velocity of a black hole, while the particle horizon is determined by the finite speed of light and the age of the universe. The particle horizon gives us a sense of the size of the observable universe, currently estimated to be about 46.5 billion light-years in radius. This size reflects the furthest distance from which light has traveled to Earth since the beginning of the universe. The event horizon's significance lies in its impact on the behavior of matter and light near black holes. It creates a boundary that fundamentally alters our understanding of space, time, and gravity. Studying event horizons helps physicists test theories of general relativity and quantum mechanics. The particle horizon, by defining the observable universe, sets the limits for our observations and measurements in cosmology. It influences how we interpret the large-scale structure of the universe and the distribution of galaxies and cosmic background radiation. Understanding the difference between these horizons is crucial for grasping the nature of our universe. The event horizon deals with the local effects of gravity and black holes, while the particle horizon encompasses the entire observable cosmos and its history. The concept of the event horizon has led to profound discoveries, such as Hawking radiation, which predicts that black holes can emit radiation and eventually evaporate. This phenomenon challenges our understanding of thermodynamics and quantum theory. The particle horizon helps cosmologists understand the universe's expansion and the distribution of matter. Observations within this horizon provide data to refine models of cosmic evolution and the influence of dark matter and dark energy. Both horizons are essential for different aspects of cosmology. The event horizon helps us understand the extreme environments near black holes, while the particle horizon shapes our understanding of the universe's observable limits and large-scale structure. As technology advances, we may learn more about these horizons. Improved observations of black holes and the cosmic microwave background will enhance our understanding of both event horizons and particle horizons, providing deeper insights into the nature of the universe. In summary, the event horizon and particle horizon represent different boundaries in cosmology. The event horizon is associated with black holes and the limits of escape, while the particle horizon defines the observable universe's edge. Understanding both is essential for a comprehensive view of the cosmos. The cosmic horizon sets the limits of what we can observe in the universe. Anything beyond this horizon remains unobservable, as its light has not had time to reach us. This limitation shapes our understanding of the cosmos. The particle horizon helps define the observable universe, providing a framework for studying its structure and evolution. Observations within this boundary offer insights into the distribution of galaxies, dark matter, and cosmic background radiation. The event horizon of a black hole marks the boundary where information is lost to the outside observer. This poses challenges for understanding the internal mechanics of black holes and their ultimate fate. Observing phenomena near event horizons tests the limits of our physical theories. Gravitational lensing near event horizons can distort our observations of distant objects. This effect allows us to study the mass and structure of black holes indirectly. It also provides a unique view of light, bending in extreme gravitational fields. The particle horizon affects how we interpret cosmic microwave background radiation. This radiation comes from near the edge of the observable universe, giving us a snapshot of the early cosmos. Studying it helps refine models of the universe's origin and development. As the universe expands, the particle horizon grows, allowing us to observe more distant regions over time. This expansion reveals new galaxies and cosmic phenomena, continuously expanding our understanding of the universe's vastness. Dark energy and the accelerating expansion of the universe impact our observations of the cosmic horizon. They influence the rate at which the observable universe grows, affecting our ability to study distant objects. Understanding this expansion is crucial for cosmology. The event horizon's effects on light and matter provide tests for theories of general relativity and quantum mechanics. Observations of these effects help scientists explore the nature of gravity and space-time in extreme conditions. This research pushes the boundaries of theoretical physics. Advanced telescopes and observatories are crucial for studying phenomena near event and particle horizons. Instruments like the Event Horizon Telescope and space-based observatories enable detailed observations of these boundaries. They enhance our ability to explore the universe's most extreme environments. Cosmic inflation theories predict that regions beyond the particle horizon may have different physical properties. Observations within our horizon provide clues about these regions, though direct study remains impossible. This understanding shapes our models of the early universe. Observing the universe's expansion and the growth of the particle horizon informs us about the rate of cosmic acceleration. It helps refine measurements of the Hubble constant and dark energy's influence. These observations are key to understanding the universe's future. The cosmic horizon's limitations remind us that our view of the universe is inherently incomplete. While we can infer much about the cosmos beyond this horizon, direct observation is beyond our current capabilities. This limitation drives the quest for new technologies and methods in astronomy. Black hole event horizons challenge our understanding of information loss and entropy. Theoretical concepts like Hawking radiation suggest that black holes may eventually evaporate, releasing information. Observations of such phenomena test the principles of quantum mechanics and thermodynamics. The study of both event and particle horizons inspires new scientific questions and theories. These boundaries push the limits of our knowledge and technological capabilities. They drive innovation in observational techniques and theoretical models. In summary, the cosmic horizon and event horizon have profound implications for our observations and understanding of the universe. They define the limits of what we can see and measure, shaping our exploration of the cosmos. Observations near these boundaries continue to challenge and expand our knowledge of the universe. Look-back time is the concept that allows us to see the universe as it was in the past. When we observe distant objects, we are looking back in time because light takes time to travel across space. The farther away an object is, the older the light we observe. This concept helps astronomers study the history and evolution of the universe. By observing galaxies at different distances, we can piece together how they formed and evolved over billions of years. Each observation provides a glimpse into a different era of the cosmic timeline. Look-back time is measured in billions of years, corresponding to the light travel time from distant objects to Earth. For example, observing a galaxy 10 billion light-years away shows us the galaxy as it was 10 billion years ago. This allows us to study the universe's past in great detail. The further we look, the closer we get to observing the conditions of the early universe. Observing the cosmic microwave background, for instance, shows us the universe when it was only 380,000 years old. This radiation is a key piece of evidence for the Big Bang theory. Look-back time also helps us understand the formation and evolution of structures in the universe. By comparing distant young galaxies with nearby older ones, we can track changes in their shapes, sizes, and compositions over time. This helps us build a timeline of cosmic events. Observing distant supernovae with significant look-back times has provided evidence for the accelerated expansion of the universe. These observations support the existence of dark energy, which drives this acceleration. The study of supernovae at different look-back times is crucial for understanding dark energy. Look-back time is essential for studying the life cycles of stars. By observing star clusters at various distances, astronomers can see different stages of stellar evolution. This information helps refine models of how stars form, evolve, and eventually die. The concept also plays a role in understanding the ionization era, a period when the first stars and galaxies ionize the intergalactic medium. Observing galaxies from this time helps us learn about the early universe and the formation of the first cosmic structures. Look-back time affects how we interpret observations of active galactic nuclei and quasars. These energetic objects provide information about the growth of supermassive black holes and the environments of early galaxies. Studying them at different look-back times reveals their evolution. Gravitational lensing allows us to observe objects at significant look-back times with greater detail. Lensing magnifies distant galaxies, making it possible to study them more closely. This technique helps us observe the early universe in more detail than otherwise possible. Look-back time also provides context for understanding galaxy collisions and mergers. Observing these events at different stages helps us see how they influence galaxy evolution. These interactions play a critical role in shaping galaxy structures over time. By studying the light from distant objects, we can infer the conditions of the early universe. This includes the distribution of matter, the influence of dark matter and dark energy, and the processes that led to galaxy formation. Look-back time is a window into these ancient processes. The concept of look-back time underscores the finite speed of light and the vast scales of the universe. It highlights the interplay between distance and time in our observations. This relationship is fundamental to our understanding of cosmology. Advances in telescope technology and observational techniques continue to push the boundaries of look-back time. New instruments allow us to observe farther and thus look further back in time. Each advancement brings new insights into the history and evolution of the universe. In summary, look-back time is a powerful tool in astronomy. It enables us to observe the universe's past, study the evolution of cosmic structures, and understand the fundamental processes that shape the cosmos. As we develop better observational capabilities, our understanding of look-back time and its implications will continue to grow. Future expansion and horizons of the universe are shaped by the dynamics of dark energy. As dark energy drives the accelerated expansion, distant galaxies will continue to move away from us at increasing speeds. This acceleration means that over time, more regions of the universe will become unreachable. Eventually, the expansion may cause distant galaxies to move beyond the cosmic horizon. Once they cross this boundary, their light will never reach us, effectively removing them from the observable universe. This leads to a shrinking observable universe, despite the universe itself continuing to expand. The future expansion of the universe depends on the properties of dark energy. If dark energy remains constant, the universe will expand indefinitely. This scenario, known as the Big Freeze, predicts a cold, dark, and isolated future as galaxies drift apart. Alternatively, if dark energy increases over time, the universe could face a Big Rip. In this scenario, the expansion accelerates so rapidly that galaxies, stars, and even atoms are torn apart. This dramatic end would occur in a finite amount of time, leading to a universe devoid of structure. The fate of the universe also depends on the interplay between dark energy and dark matter. While dark energy drives expansion, dark matter's gravitational pull works to slow it down. Understanding this balance is crucial for predicting the universe's long-term behavior. Observations of the cosmic microwave background and distant supernovae provide data on the expansion rate and dark energy's properties. These observations help refine our models of future expansion. Continued monitoring of cosmic expansion will enhance our understanding of dark energy's role. Advanced telescopes and space missions will play a key role in studying the universe's expansion. Projects like the James Webb Space Telescope will observe distant galaxies and supernovae, providing more accurate measurements of the expansion rate. These missions will deepen our understanding of cosmic horizons. Gravitational wave observatories will also contribute to our knowledge of cosmic expansion. By detecting waves from distant events, these observatories can provide independent measurements of the expansion rate. This data complements observations of light and deepens our understanding of the universe's dynamics. As the universe expands, the cosmic microwave background will continue to cool and stretch to longer wavelengths. This redshifting of the CMB will eventually make it undetectable by current instruments. Future observatories will need to be sensitive to these lower energy signals to study the far future universe. The growth of the particle horizon will continue, allowing us to see regions that were previously beyond our observational reach. However, the increasing distance to these regions will also make them fainter and harder to study. Advanced technology will be necessary to observe these distant parts of the universe. The future of cosmic horizons involves not just understanding physical distances, but also the limits of human observation. Technological advancements will extend our horizons, but there will always be fundamental limits imposed by the nature of light and the universe's expansion. The concept of cosmic horizons also raises philosophical questions about the ultimate fate of the universe. As we study these boundaries, we gain insights into the universe's past, present, and potential future. These questions drive ongoing research and exploration. In the distant future, galaxies within gravitationally bound groups, like our local group, will remain together. However, other galaxies will recede beyond the cosmic horizon, becoming unobservable. This isolation will shape the future cosmic landscape. Understanding future expansion and horizons helps us grasp the full scope of cosmic evolution. It informs us about the long-term fate of cosmic structures and the universe's ultimate destiny. This knowledge is crucial for building a comprehensive picture of the cosmos. In summary, the future expansion of the universe and the concept of horizons are deeply interconnected. Dark energy, cosmic expansion, and advanced observations all play roles in shaping our understanding of these phenomena. As we continue to explore the universe, we will uncover more about its vast and dynamic nature. Models of the universe describe its overall shape and fate. These models are based on the geometry of space and the balance between gravity and the expansion force. The three main models are flat, open, and closed. A flat universe means that space is Euclidean, with parallel lines never converging or diverging. This model suggests the universe will expand forever, but the expansion rate will gradually slow down. Current observations, including the cosmic microwave background, support a flat universe. An open universe has a hyperbolic geometry, meaning it is negatively curved like a saddle. In this model, the universe will expand forever, with the expansion rate not slowing as much as in a flat universe. This scenario implies an ever-thinning, colder universe. A closed universe has a spherical geometry, meaning it is positively curved like the surface of a sphere. This model suggests that the universe could eventually stop expanding and start contracting, leading to a big crunch. This cyclical nature implies a universe with a finite lifespan. The geometry of the universe is determined by its total energy density. If the density is exactly equal to the critical density, the universe is flat. If the density is greater than the critical density, the universe is closed. If it is less, the universe is open. The critical density is the specific density at which the universe is perfectly balanced between expanding forever and eventually collapsing. It is a crucial parameter in cosmology, defining the geometry and fate of the universe. Current measurements suggest the universe is very close to this critical density. Dark energy plays a significant role in determining the universe's fate. Even in a flat universe, dark energy causes accelerated expansion. This mysterious force influences all models, altering their long-term predictions. The flat model is the most supported by current data. Observations of the cosmic microwave background, galaxy distributions, and supernovae all indicate a universe that is very close to flat. This model aligns with the predictions of cosmic inflation. In the open model, the universe's negative curvature leads to distinct observational signatures. Galaxies appear smaller at great distances, and the cosmic microwave background shows different patterns compared to a flat universe. However, current data do not strongly support this model. The closed model implies a finite universe. possibly leading to a future contraction. This cyclical model raises intriguing possibilities about the universe's past and future. Observations currently suggest our universe is not closed, but understanding this model provides insight into potential cosmic behaviors. Inflationary theory predicts a flat universe. During the rapid expansion of inflation, any initial curvature would be stretched to near flatness. This prediction has been confirmed by precise measurements of the cosmic microwave background. The shape of the universe affects the ultimate fate of cosmic structures. In a flat or open universe, galaxies will continue to drift apart, becoming isolated. In a closed universe, galaxies could eventually merge back together in a collapsing cosmos. Understanding these models helps us grasp fundamental questions about the universe's origin, structure, and destiny. Each model provides a framework for exploring different aspects of cosmic evolution. Observational data and theoretical work continue to refine our understanding. Future observations, particularly of the cosmic microwave background and large-scale structure, will further clarify the universe's shape. Advanced telescopes and missions will provide more precise measurements, helping to determine which model best describes our cosmos. In summary, the models of the universe, flat, open, and closed, offer different perspectives on its geometry and fate. Current evidence strongly supports a flat universe, driven by dark energy. Continued research and observations will deepen our understanding of these models and their implications for the cosmos. Multiverse theories propose that our universe is just one of many universes that exist. These multiple universes together form a multiverse, each with its own distinct properties and laws of physics. The concept challenges our traditional understanding of space and reality. One type of multiverse theory is the bubble universe theory. It suggests that different regions of space could undergo different rates of inflation, leading to bubbles that become separate universes. Each bubble could have its own physical constants and laws. String theory also supports the idea of a multiverse. According to string theory, there are many possible ways to compactify extra dimensions. Each compactification corresponds to a different vacuum state, potentially creating a vast number of distinct universes. The many worlds interpretation of quantum mechanics introduces another form of the multiverse. It proposes that every quantum event spawns multiple branching universes. In this view, all possible outcomes of quantum measurements are realized in separate, non-communicating branches. The anthropic principle is often invoked in multiverse discussions. It suggests that we observe the universe's properties as they are because only certain universes can support life. This principle can explain why the physical constants of our universe appear fine-tuned for life. Cosmic inflation naturally leads to the idea of a multiverse. The rapid expansion of space during inflation could create isolated regions that stop inflating at different times. Each region could evolve into a separate universe with its own characteristics. Some multiverse theories predict different laws of physics in each universe. These variations could include different strengths of fundamental forces, different particles, or entirely different dimensions. This diversity makes the multiverse concept both fascinating and complex. Observational evidence for a multiverse is challenging to obtain. Since other universes would be outside our observable horizon, direct evidence is difficult to acquire. However, certain patterns in the cosmic microwave background could hint at interactions with other universes. The idea of a multiverse has significant philosophical implications. It challenges the notion of a singular, unique universe and raises questions about the nature of reality. The existence of multiple universes suggests a broader and more complex cosmos than previously imagined. Critics argue that multiverse theories are untestable and therefore not scientific. They claim that without empirical evidence, the multiverse remains a speculative concept. Proponents, however, argue that indirect evidence and consistency with existing theories lend credibility to the idea. The concept of a multiverse also appears in popular culture. It has been featured in science fiction literature, movies, and television shows, capturing the imagination of the public. These depictions often explore the consequences of parallel realities and alternate histories. Multiverse theories can potentially solve certain puzzles in cosmology. They provide explanations for the fine-tuning of physical constants and the initial conditions of the universe. By considering a vast number of universes, these theories offer new perspectives on old problems. Theoretical physicists continue to explore the implications of a multiverse. Research in string theory, quantum mechanics and cosmology provides ongoing insights into the plausibility of multiple universes. These investigations push the boundaries of our understanding. Future advancements in technology and observations may shed more light on the multiverse concept. Improved measurements of the cosmic microwave background and gravitational waves could offer indirect evidence. Theoretical breakthroughs might also provide new ways to test multiverse hypotheses. In summary, multiverse theories suggest the existence of multiple universes with diverse properties. These theories arise from ideas in inflation, string theory, and quantum mechanics. While challenging to test, the concept of a multiverse expands our understanding of the cosmos and its fundamental nature. String theory is a theoretical framework that attempts to unify all fundamental forces of nature. It proposes that the basic building blocks of the universe are not point particles, but one-dimensional strings. These strings can vibrate at different frequencies, giving rise to various particles. One of the most intriguing aspects of string theory is the requirement for extra dimensions. While we experience the universe in three spatial dimensions, string theory suggests there could be additional dimensions that are compactified or curled up at very small scales. These extra dimensions are essential for the mathematical consistency of the theory. In string theory, the different vibrational modes of strings correspond to different particles. For instance, the graviton, which mediates the force of gravity, is one of these vibrational modes. This feature makes string theory a candidate for a theory of everything, unifying gravity with the other fundamental forces. The compactification of extra dimensions can take many forms, leading to a variety of possible universes with different physical properties. The specific way in which dimensions are compactified determines the characteristics of the resulting universe. This flexibility is both a strength and a challenge for string theory. String theory predicts the existence of multiple types of strings, such as open strings with endpoints and closed strings forming loops. These different types of strings can interact in complex ways, producing a rich spectrum of particles and forces. Understanding these interactions is key to unlocking the full potential of string theory. Extra dimensions in string theory are often visualized as tiny, compact shapes like circles or more complex manifolds. These shapes are incredibly small, much smaller than an atom, making them difficult to detect directly. However, their effects can influence the behavior of particles and forces in our familiar three-dimensional space. The idea of extra dimensions is not entirely new. It has roots in earlier theories, such as Kaluza-Klein theory, which proposed a fifth dimension to unify gravity and electromagnetism. String theory builds on these ideas, extending them to a more comprehensive framework. Testing string theory and its predictions about extra dimensions is a significant challenge. While direct detection of extra dimensions is currently beyond our technological capabilities, indirect evidence might be found through high-energy particle experiments, such as those conducted at the Large Hadron Collider. String theory also introduces the concept of branes, multidimensional objects on which strings can attach. These branes can exist in various dimensions and play a crucial role in the dynamics of the theory. Our universe might be a three-dimensional brane embedded in a higher dimensional space. The mathematical elegance of string theory is one of its most appealing features. It provides a consistent framework for describing all known particles and forces, including gravity. This mathematical beauty suggests that string theory could be a fundamental theory of nature, despite the lack of direct experimental evidence so far. String theory has led to many important developments in theoretical physics. It has provided insights into black hole thermodynamics, the holographic principle, and the nature of space-time. These contributions have deepened our understanding of the universe, even if string theory itself remains unproven. The landscape of possible solutions in string theory, known as the string landscape, is vast. It includes an enormous number of potential universes, each with its own set of physical laws. This diversity raises questions about why our particular universe has the properties it does, a question that intertwines with the anthropic principle. The quest to understand extra dimensions and string theory continues to inspire physicists. New approaches and ideas are constantly being explored, pushing the boundaries of our knowledge. Advances in technology and experimental techniques may one day provide the evidence needed to confirm or refute string theory. String theory's potential to unify all forces makes it a highly attractive area of research. Its implications for our understanding of the universe are profound, offering a glimpse into the fundamental nature of reality. As research progresses, we may uncover more about the hidden dimensions that shape our world. In summary, string theory and the concept of extra dimensions offer a promising framework for unifying the fundamental forces of nature. While challenging to test, these ideas continue to drive theoretical and experimental advancements in physics. The exploration of these concepts holds the potential to revolutionize our understanding of the universe. Quantum mechanics, typically applied to the microscopic world, also has implications at cosmic scales. The principles of quantum mechanics, such as wave-particle duality and uncertainty, extend to the behavior of particles in the early universe. These effects influence the formation and evolution of cosmic structures. One key concept is quantum fluctuations. During the inflationary period of the early universe, tiny quantum fluctuations were stretched to macroscopic scales. These fluctuations seeded the formation of galaxies and large-scale structures, leaving imprints in the cosmic microwave background. The idea that quantum mechanics can impact large-scale structures challenges our classical understanding of the universe. It suggests that the fundamental randomness and uncertainty of quantum processes play a crucial role in shaping the cosmos. This interplay between quantum mechanics and cosmology is a fascinating area of study. Quantum entanglement, another principle of quantum mechanics, could have cosmic implications. If particles that are light years apart are entangled, their states remain correlated regardless of the distance. This phenomenon raises questions about the nature of information transfer across vast distances. Black holes provide a unique arena for studying quantum mechanics on cosmic scales. The concept of Hawking radiation, which arises from quantum effects near the event horizon, suggests that black holes can emit particles and eventually evaporate. This idea merges quantum mechanics with general relativity. The information paradox related to black hole evaporation is a profound issue where quantum mechanics and gravity intersect. It questions what happens to the information about the matter that falls into a black hole. Resolving this paradox could lead to new insights into quantum gravity. String theory, which incorporates quantum mechanics, aims to unify all fundamental forces, including gravity. It suggests that space-time itself has a quantum structure at the smallest scales. This theory predicts the existence of extra dimensions and provides a framework for understanding quantum effects in the cosmos. The study of quantum field theory in curved space-time explores how quantum fields behave in the presence of strong gravitational fields, such as near black holes. This approach helps in understanding phenomena like Hawking radiation and the behavior of particles in extreme environments. Quantum mechanics also influences our understanding of the early universe. Theories such as quantum cosmology attempt to describe the universe's origin in quantum terms. These theories suggest that the universe may have emerged from a quantum fluctuation. Quantum tunneling, a process where particles pass through energy barriers they classically shouldn't, might explain certain cosmic phenomena. For instance, tunneling could have played a role in the rapid expansion of the universe during inflation. Understanding these processes sheds light on the universe's earliest moments. The concept of the multiverse, arising from both string theory and quantum mechanics, proposes that our universe is just one of many. Quantum events could lead to the creation of multiple, parallel universes with different properties. This idea challenges our perception of reality and the uniqueness of our universe. Experimental advances in quantum technology could one day provide new ways to test these theories. Technologies such as quantum computers and ultra-sensitive detectors may reveal subtle quantum effects on cosmic scales. These advancements hold the potential to bridge the gap between quantum mechanics and cosmology. The holographic principle, a concept derived from string theory and quantum mechanics, suggests that the information content of a region of space can be described by its boundary. This principle has implications for understanding black holes and the nature of space-time. It points to a deeper connection between quantum information and gravity. Exploring the connections between quantum mechanics and cosmology requires new theoretical and experimental approaches. Interdisciplinary research is crucial for advancing our understanding of these complex and interconnected domains. As we develop better tools and theories, we may uncover new insights into the fundamental nature of the universe. In summary, quantum mechanics at cosmic scales reveals the deep connections between the smallest and largest structures in the universe. From quantum fluctuations shaping galaxies to the behavior of black holes, these principles challenge our classical understanding and open new avenues for exploration. The intersection of quantum mechanics and cosmology continues to be a rich field of study with profound implications. The edge of the universe has different meanings in various cosmological theories. In the standard Big Bang model, there is no physical edge. The universe is finite but unbounded, much like the surface of a sphere. This concept suggests that if you travel far enough in one direction, you would eventually return to your starting point. In the context of multiverse theories, the edge could represent the boundary of our observable universe, beyond which other distinct universes exist. These universes could have different physical laws and constants, making the edge a transition between different realms of reality. String theory proposes that the edge might be a boundary where our three-dimensional universe intersects with higher dimensional spaces or branes. These branes can interact, potentially leading to phenomena observable in our universe. The edge, in this sense, is a higher dimensional boundary. Quantum mechanics introduces the idea of quantum fluctuations at the edge of the observable universe. These fluctuations could give rise to new universes in a never-ending cycle of creation. The edge here represents the frontier of our observable cosmos, influenced by quantum processes. Inflationary theory suggests that the edge of our observable universe marks the limit of the region that underwent inflation. Beyond this edge, conditions could be vastly different, possibly leading to other inflationary regions or bubble universes. The edge is the end of our inflated patch of space. In a closed universe model, the edge would be where the universe curves back on itself, creating a finite but unbounded space. This model implies a universe that is self-contained with no physical boundaries, emphasizing the concept of a curved space-time. In an open universe model, the edge is more abstract, representing the limit of our observational capabilities rather than a physical boundary. The universe would continue infinitely, but the observable part is limited by the speed of light and the age of the universe. Some theories propose a holographic principle, where the edge of the universe could be a boundary that encodes all the information within. This principle suggests that our three-dimensional universe is a projection of information stored on a distant two-dimensional surface. The concept of a cosmic event horizon introduces an edge defined by the farthest distance from which light can ever reach us. Beyond this horizon, events cannot influence us, marking a practical boundary for observation and interaction. The edge in loop quantum gravity might be where classical spacetime breaks down into discrete quantum units. This theory suggests a fundamentally granular structure of space at the smallest scales, with the edge being the transition point between smooth and quantum granular space. Some speculative theories consider the edge of the universe as a membrane separating different phases of the cosmos, akin to a phase transition. This membrane could represent a change in the fundamental properties of space and time, leading to different physical realities. In brain world scenarios, the edge could be where our three-dimensional brain intersects with higher dimensional bulk space. This interaction could allow for the transfer of energy or information between different dimensions, making the edge a portal to higher dimensions. The idea of a cyclic universe suggests that the edge marks the end of one cycle of expansion and the beginning of another contraction. This cyclical model implies a universe with no ultimate beginning or end, but a continuous process of birth, evolution, and rebirth. In theories involving dark energy, the edge might be where dark energy's influence becomes dominant, accelerating the expansion of the universe. This edge represents a shift in the cosmic dynamics, where the repulsive force of dark energy overcomes gravitational attraction. Ultimately, the edge in different theories represents a boundary, where our understanding and observational capabilities reach their limits. Each theory provides a unique perspective on what lies beyond, challenging our concepts of space, time, and reality. Exploring these edges helps push the boundaries of our knowledge, offering insights into the fundamental nature of the universe. Dark matter is a mysterious substance that makes up about 27% of the universe's mass energy content. Unlike normal matter, it does not emit, absorb, or reflect light, making it invisible to current instruments. Its presence is inferred from gravitational effects on visible matter, radiation, and the large-scale structure of the universe. The concept of dark matter emerged to explain discrepancies in the rotational speeds of galaxies. Observations showed that galaxies rotate faster than expected, based on visible mass alone. This implied the existence of an unseen mass providing additional gravitational pull. Dark matter also plays a crucial role in the formation and evolution of cosmic structures. It acts as a gravitational scaffold, attracting normal matter and leading to the formation of galaxies and clusters. Without dark matter, the universe's large-scale structure would be vastly different. Several lines of evidence support the existence of dark matter. Observations of galaxy clusters, gravitational lensing, and the cosmic microwave background all indicate its presence. These observations consistently show that dark matter is 5 times more abundant than normal matter. Gravitational lensing provides a direct way to map dark matter. When light from distant objects passes near massive clusters, it is bent, creating distorted and magnified images. The degree of lensing reveals the mass distribution, including the unseen dark matter. The nature of dark matter remains one of the biggest mysteries in cosmology. It could consist of unknown particles that do not interact with electromagnetic forces. These particles would interact primarily through gravity, making them difficult to detect directly. Several candidates for dark matter particles have been proposed. Weakly interacting massive particles, or WIMPs, are one possibility. These hypothetical particles interact via the weak nuclear force and gravity, making them a leading candidate in dark matter research. Another candidate is the axion, a very light particle that could account for dark matter. Axions are predicted by certain extensions of the standard model of particle physics. They would interact very weakly with normal matter, making them elusive. Massive, compact halo objects, or machos, are another proposed form of dark matter. These include objects like black holes, neutron stars, and brown dwarfs that do not emit much light. However, searches for machos have not found enough to account for all dark matter. Direct detection experiments aim to identify dark matter particles by observing their interactions with normal matter. These experiments are typically conducted deep underground to shield them from cosmic rays and other background noise. So far, no direct detections have been confirmed. Indirect detection searches for the products of dark matter interactions, such as gamma rays or neutrinos. Instruments like the Fermi Gamma Ray Space Telescope look for signals that could indicate dark matter annihilation or decay. These efforts are ongoing and have yet to yield definitive results. Dark matter also plays a role in galaxy formation. Simulations show that dark matter clumps together under gravity, forming halos in which galaxies can form. These halos provide the gravitational wells necessary for accumulating gas and forming stars. Understanding dark matter is crucial for a complete picture of the universe. It influences cosmic evolution, the behavior of galaxies, and the distribution of matter. Solving the mystery of dark matter would significantly advance our knowledge of fundamental physics. The search for dark matter continues to be a major focus in both astrophysics and particle physics. New experiments, observations, and theoretical models aim to uncover its nature. As technology advances, we may come closer to revealing the secrets of this enigmatic substance. In summary, dark matter is an invisible and mysterious component of the universe. It is crucial for explaining gravitational effects and the large-scale structure of the cosmos. Despite extensive research, its true nature remains unknown, making it one of the most intriguing topics in modern science. Evidence for dark matter comes from various astronomical observations. One of the earliest pieces of evidence was the rotation curves of galaxies. Observations showed that stars in the outer regions of galaxies rotate at speeds that cannot be explained by the visible matter alone. Gravitational lensing provides another line of evidence. When light from a distant galaxy passes near a massive object like a galaxy cluster, it bends, creating multiple images or arcs. The amount of lensing observed cannot be accounted for by visible matter alone, indicating the presence of dark matter. Galaxy cluster observations also support the existence of dark matter. The mass of clusters, calculated from the motions of galaxies within them, and the hot gas between galaxies, exceeds the mass of visible matter. This discrepancy suggests a significant amount of unseen mass. The cosmic microwave background radiation offers further evidence. Small fluctuations in this radiation provide a snapshot of the early universe. These fluctuations match the predictions made by models that include dark matter, supporting its existence. The Bullet Cluster is a compelling case study. It consists of two colliding galaxy clusters. Observations of the Bullet Cluster show a separation between the normal matter, seen in X-ray images, and the dark matter, inferred from gravitational lensing. This separation provides strong evidence for dark matter. The large-scale structure of the universe observed through galaxy surveys aligns with dark matter models. Simulations of the universe's evolution, including dark matter, accurately reproduce the distribution and clustering of galaxies seen today. These simulations would not match observations without dark matter. The behavior of hot gas in galaxies and clusters also indicates dark matter. The temperature and distribution of this gas suggest more mass than is visible. Dark matter provides the additional gravitational pull needed to keep this gas bound to galaxies and clusters. Measurements of the mass-to-light ratio in galaxies and clusters reveal dark matter. This ratio compares the total mass to the amount of light emitted. The observed ratios are much higher than what can be explained by visible matter alone, implying a substantial dark matter component. Weak gravitational lensing studies, which measure the slight distortions of background galaxies by foreground mass, support dark matter. These distortions reveal the presence of mass that does not emit light, consistent with dark matter's gravitational effects. The cosmic web, the large-scale structure of the universe, is shaped by dark matter. Observations and simulations show that dark matter forms the backbone of this web, influencing the distribution of galaxies and clusters. Without dark matter, the cosmic web structure would be significantly different. The Sunyaev-Zeldovich effect, which measures the distortion of the cosmic microwave background by hot gas in galaxy clusters, also indicates dark matter. This effect helps estimate the total mass of clusters, revealing more mass than visible matter alone can account for. Galactic rotation curves, gravitational lensing, galaxy clusters, cosmic microwave background, bullet cluster, large-scale structure, hot gas behavior, mass-to-light ratios, weak gravitational lensing, cosmic web, and the Sunyaev-Zeldovich effect all provide evidence for dark matter. Each of these observations points to a consistent conclusion. There is more mass in the universe than what we can see. Dark matter, though invisible, exerts a significant gravitational influence on cosmic structures. This unseen matter is essential for explaining a wide range of astrophysical phenomena. Ongoing research and observations aim to further understand dark matter. Future experiments may provide more direct evidence or even detect dark matter particles. As we continue to explore the universe, the mystery of dark matter remains a central focus of scientific inquiry. Dark energy is a mysterious force driving the accelerated expansion of the universe. It makes up about 68% of the universe's total energy content. Unlike dark matter, dark energy is not associated with mass and does not clump together under gravity. The discovery of dark energy was made through observations of distant Type Ia supernovae. These supernovae are used as standard candles to measure cosmic distances. Observations showed that these supernovae were dimmer than expected, indicating that the universe's expansion is speeding up. Dark energy's nature is still largely unknown. It could be a property of space itself, often described by the cosmological constant introduced by Einstein. The cosmological constant suggests that dark energy's density remains constant over time, driving accelerated expansion. Another possibility is that dark energy is a dynamic field, changing over time. This idea is known as quintessence. Unlike the cosmological constant, quintessence varies, potentially leading to different expansion rates at different times in the universe's history. The effect of dark energy becomes more significant as the universe expands. As galaxies move further apart, dark energy's repulsive force overcomes the attractive force of gravity. This results in the accelerated expansion we observe today. The accelerated expansion has profound implications for the fate of the universe. If dark energy continues to dominate, the universe could expand forever, leading to a cold, dark, and empty cosmos. This scenario is often referred to as the Big Freeze. Dark energy also affects the large-scale structure of the universe. It influences the formation and growth of galaxies and clusters. By studying the distribution of galaxies, scientists can learn more about dark energy's properties and effects. Observations of the cosmic microwave background provide evidence for dark energy. The patterns in this radiation reflect the universe's composition, including the influence of dark energy. These observations help refine models of cosmic evolution. The integrated Sachs-Wolf effect offers another line of evidence. This effect occurs when cosmic microwave background photons travel through large-scale gravitational potentials affected by dark energy. It provides a way to study dark energy's influence on the cosmic microwave background. The study of baryon acoustic oscillations helps measure the universe's expansion history. These oscillations are imprinted in the distribution of galaxies and provide a standard ruler for measuring cosmic distances. Observations of these oscillations help constrain dark energy's properties. Future missions aim to better understand dark energy. Projects like the Euclid satellite and the Dark Energy Survey are designed to study the universe's expansion and the distribution of galaxies. These missions will provide more data to refine our understanding of dark energy. Theoretical models of dark energy explore various possibilities, from modifications of general relativity to entirely new fields and particles. These models aim to explain dark energy's origin and behavior. Testing these models requires precise observations and advanced technology. The search for dark energy's true nature continues to drive advancements in cosmology and astrophysics. It is one of the most significant challenges in understanding the universe. Solving the mystery of dark energy would profoundly impact our knowledge of cosmic evolution and fundamental physics. Understanding dark energy is crucial for a complete picture of the universe. It influences the past, present, and future of cosmic expansion. As we gather more data and refine our models, we may come closer to uncovering the secrets of this enigmatic force. In summary, dark energy is a mysterious force responsible for the universe's accelerated expansion. It makes up a significant portion of the universe's energy content and has far-reaching implications for cosmic evolution. Continued research and observation aim to uncover its true nature and effects. Experiments and observations are crucial for understanding the universe. Telescopes and space missions provide data on cosmic phenomena, revealing insights about dark matter, dark energy, and the large-scale structure of the cosmos. These tools allow scientists to test theories and refine models. The Hubble Space Telescope has revolutionized our view of the universe. By capturing detailed images of distant galaxies, Hubble has helped measure the rate of expansion and provided evidence for dark energy. Its observations have been pivotal in many astronomical discoveries. The Planck satellite has mapped the cosmic microwave background with high precision. This data offers a snapshot of the early universe, showing temperature fluctuations that indicate the presence of dark matter and dark energy. Planck's findings have refined our understanding of the universe's composition and evolution. The Large Hadron Collider, LHC, explores the fundamental particles and forces that make up the universe. By colliding particles at high energies, the LHC searches for evidence of dark matter particles and tests theories like supersymmetry. These experiments probe the smallest scales of the cosmos. The Dark Energy Survey, DES, aims to understand dark energy by mapping hundreds of millions of galaxies. By studying the distribution of galaxies and measuring cosmic distances, DES helps constrain the properties of dark energy and its impact on cosmic expansion. The Euclid satellite, set to launch soon, will map the geometry of the dark universe. It will survey billions of galaxies, measure the distribution of dark matter, and investigate the nature of dark energy. Euclid's mission will provide crucial data for understanding cosmic acceleration. Gravitational wave observatories like LIGO and Virgo detect ripples in space-time caused by massive cosmic events. These observations open a new window into the universe, providing information about black holes, neutron stars, and potentially dark matter. Gravitational waves complement electromagnetic observations. The James Webb Space Telescope, JWST, will study the universe in infrared light. JWST will observe the first galaxies, star formation, and the atmospheres of exoplanets. Its advanced capabilities will extend our understanding of the universe's history and structure. Radio telescopes such as the Very Large Array, VLA, observe cosmic phenomena at radio wavelengths. These observations reveal details about galaxy formation, pulsars, and the cosmic microwave background. Radio astronomy helps study regions of space obscured by dust in visible light. Ground-based observatories like the Subaru telescope continue to provide valuable data. These observatories conduct wide field surveys, searching for distant supernovae, mapping galaxy clusters, and studying the large-scale structure of the universe. They complement space-based observations. Neutrino detectors, such as IceCube, observe high-energy neutrinos from cosmic sources. Neutrinos provide unique information about processes like supernovae and gamma-ray bursts. These elusive particles offer insights into the universe's most energetic events. Cosmic microwave background experiments like the Atacama Cosmology Telescope study the universe's oldest light. These observations help refine models of the early universe, measure the Hubble constant, and test theories of inflation. They are essential for understanding the universe's initial conditions. Dark matter detection experiments, such as the Xenon 1T detector, search for direct interactions with dark matter particles. These experiments are located deep underground to shield them from background radiation. They aim to identify dark matter particles and understand their properties. Future missions and experiments will further our understanding of the universe. Projects like the Square Kilometre Array, SKA, will provide unprecedented sensitivity in radio astronomy, while next-generation gravitational wave detectors will observe a broader range of cosmic events. In summary, experiments and observations are fundamental to advancing our knowledge of the universe. From telescopes to particle colliders, these tools provide critical data that shape our understanding of cosmic phenomena. Continued advancements in technology and observational techniques promise to reveal even more about the cosmos. These experiments and observations have profoundly impacted our understanding of the universe. They have confirmed key aspects of the Big Bang theory, revealing a universe that has been expanding and evolving over billions of years. This evidence has shaped our cosmological models. Observations of cosmic microwave background radiation have provided a snapshot of the universe when it was just 380,000 years old. This data has refined our estimates of the universe's age, composition, and rate of expansion. It supports the theory of inflation and the presence of dark matter and dark energy. The discovery of dark energy and the accelerated expansion of the universe has revolutionized cosmology. It has introduced new questions about the nature of the cosmos and the ultimate fate of the universe. Understanding dark energy remains one of the most significant challenges in physics. Mapping the large-scale structure of the universe has shown us the intricate web of galaxies and clusters. This cosmic web is shaped by the gravitational effects of dark matter, providing strong evidence for its existence. These maps have deepened our understanding of how structures in the universe form and evolve. The detection of gravitational waves has opened a new window into the universe. These waves allow us to observe events that are invisible in traditional electromagnetic spectrum, such as black hole mergers. They provide new insights into the behavior of gravity and the nature of compact objects. Studies of galaxy rotation curves have revealed the presence of dark matter. These observations show that galaxies contain much more mass than what we can see. Dark matter's gravitational effects are crucial for explaining these rotation speeds and the stability of galaxies. Observations of type Ia supernovae have provided critical evidence for the accelerating expansion of the universe. These standard candles allow us to measure cosmic distances accurately. Their dimming over time supports the presence of dark energy. High-energy particle experiments have searched for dark matter particles, though none have been definitively detected yet. These experiments are crucial for understanding the fundamental components of the universe. They help refine our models of particle physics and cosmology. The study of exoplanets has expanded our knowledge of planetary systems. Observations of planets orbiting other stars provide clues about the formation and evolution of solar systems. They raise the possibility of finding life beyond Earth, challenging our understanding of life's potential in the universe. Infrared observations have revealed details about star formation and the early universe. Telescopes like the James Webb Space Telescope will continue to uncover the hidden processes in dust-shrouded regions of space. These insights are crucial for understanding the life cycle of stars and galaxies. Neutrino observations have provided information about the most energetic and distant events in the universe. These nearly massless particles travel across vast distances, offering a unique perspective on cosmic phenomena. They help us understand processes like supernovae and the behavior of fundamental particles. Advanced radio telescopes have mapped the distribution of hydrogen in the universe, revealing the structure of galaxies and the intergalactic medium. These observations are vital for understanding the large-scale distribution of matter and the dynamics of cosmic evolution. Continued observations of the cosmic microwave background refine our understanding of the universe's initial conditions. These studies help test theories of inflation and the nature of primordial fluctuations. They are essential for developing a coherent picture of the universe's beginnings. The integration of data from different types of observations, optical, radio, infrared, gravitational waves, and more, provides a comprehensive view of the universe. This multi-messenger approach allows us to cross-verify findings and develop more accurate models of cosmic phenomena. In summary, the impact of these experiments and observations on our understanding of the universe is immense. They have confirmed fundamental theories, revealed new phenomena, and opened up exciting avenues of research. As technology and methods continue to advance, our comprehension of the universe will grow ever deeper. The cosmic web is a vast, complex structure that forms the backbone of the universe. It is composed of filaments, which are elongated strands of galaxies and dark matter. These filaments connect clusters of galaxies and create a web-like pattern across the cosmos. The formation of the cosmic web began shortly after the Big Bang. Small density fluctuations in the early universe grew under the influence of gravity, leading to the formation of these large-scale structures. Over billions of years, these structures have evolved into the intricate web we observe today. Dark matter plays a crucial role in the formation of the cosmic web. It provides the gravitational scaffolding that attracts normal matter, leading to the formation of galaxies and clusters along the filaments. Without dark matter, the cosmic web would not have formed in the same way. Observations of the cosmic web are made using various techniques. Large galaxy surveys, such as the Sloan Digital Sky Survey, map the distribution of galaxies across vast regions of space. These surveys reveal the filamentary structure of the universe and help us understand its large-scale organization. Gravitational lensing is another method used to study the cosmic web. By observing the bending of light from distant galaxies, astronomers can map the distribution of dark matter in the filaments. This technique provides a detailed view of the invisible scaffolding that shapes the universe. Hydrogen gas, the most abundant element in the universe, traces the filaments of the cosmic web. Observations of the Lyman alpha forest, a series of absorption lines in the spectra of distant quasars, reveal the distribution of hydrogen gas. These observations help map the large-scale structure of the universe. Simulations of the universe's evolution, such as those conducted by the Illustris and Millennium projects, reproduce the formation of the cosmic web. These simulations use the laws of physics to model the growth of structures over time. They provide insights into the processes that shape the universe. The intersections of filaments, known as nodes, are regions where galaxy clusters form. These clusters are the largest gravitationally bound structures in the universe. Studying the properties of clusters and their distribution helps us understand the dynamics of the cosmic web. Voids are the large, empty spaces between filaments. These regions contain very few galaxies compared to the dense filaments. The study of voids provides valuable information about the distribution of matter in the universe and the influence of dark energy on cosmic expansion. The cosmic web influences the formation and evolution of galaxies. Galaxies in dense regions of the web tend to be larger and more evolved, while those in less dense regions are smaller and younger. Understanding this relationship helps us learn about galaxy formation and evolution. The cosmic web also plays a role in the distribution of cosmic radiation. The filaments and clusters can act as gravitational lenses, magnifying and distorting the light from distant sources. This effect provides a way to study the distribution of matter on large scales. Recent observations have begun to detect the faint glow of the cosmic web in X-ray and radio wavelengths. These observations reveal the hot gas that fills the filaments and provide new insights into the structure and composition of the web. They help us understand the thermal history of the universe. The study of the cosmic web is crucial for understanding the universe's large-scale structure and evolution. It connects the formation of galaxies and clusters to the initial conditions of the universe. Research in this area continues to reveal new details about the fundamental nature of the cosmos. Future surveys and observations will provide even more detailed maps of the cosmic web. Advanced telescopes and instruments will help us see fainter and more distant structures. These efforts will improve our understanding of the universe's large-scale organization and the role of dark matter and dark energy. In summary, the cosmic web and its filaments form the universe's large-scale structure. These interconnected strands of galaxies and dark matter reveal the complex dynamics of cosmic evolution. Ongoing research and observations continue to uncover the mysteries of this vast cosmic network. Galaxy clusters are among the largest gravitationally bound structures in the universe. They consist of hundreds to thousands of galaxies, all held together by gravity. These clusters are important for studying the distribution and behavior of dark matter. Superclusters are even larger structures, consisting of multiple galaxy clusters. They can span hundreds of millions of light-years and contain tens of thousands of galaxies. Superclusters are part of the cosmic web connected by filaments of dark matter and galaxies. The center of a galaxy cluster typically contains a massive elliptical galaxy. These central galaxies are formed through the merging of smaller galaxies within the cluster. The dynamics of these central galaxies provide insights into the cluster's formation and evolution. Galaxy clusters contain large amounts of hot, X-ray emitting gas. This gas is heated to millions of degrees as galaxies move through the cluster's gravitational field. Observing the X-ray emission from this gas helps astronomers measure the cluster's total mass, including dark matter. The gravitational lensing effect is particularly strong in galaxy clusters. The massive gravitational field of a cluster bends the light from background galaxies, creating arcs and multiple images. This lensing effect is used to map the distribution of dark matter within the cluster. Superclusters are not gravitationally bound structures. They are instead large associations of galaxy clusters that are drawn together by gravity, but will eventually separate due to the universe's expansion. Studying superclusters helps understand the large-scale structure of the universe. The Virgo supercluster, which includes the local group of galaxies to which the Milky Way belongs, is an example of a supercluster. It spans over 110 million light-years and contains thousands of galaxies. Observing the Virgo supercluster provides a local perspective on these immense structures. The Sloan Great Wall is one of the largest known superclusters. It stretches over 1.37 billion light-years and contains numerous galaxy clusters. Discoveries like the Sloan Great Wall challenge our understanding of the universe's largest structures. Galaxy clusters and superclusters are crucial for studying dark energy. The distribution and motion of galaxies within these structures provide information about the universe's expansion. This data helps refine models of dark energy and cosmic acceleration. The study of galaxy clusters reveals information about galaxy formation and evolution. Galaxies in clusters experience interactions and mergers more frequently than those in isolation. These interactions can trigger star formation and affect the galaxy's morphology. Observations of the Sunyaev-Zeldovich effect in galaxy clusters provide another method for measuring their properties. This effect occurs when the cosmic microwave background radiation passes through the hot gas in a cluster, creating a distinct signal. It helps measure the cluster's total mass and structure. Clusters of galaxies serve as laboratories for studying the physics of the intergalactic medium. The hot gas in clusters can tell us about processes like cooling flows, feedback from supermassive black holes, and the enrichment of the intergalactic medium with heavy elements. Galaxy clusters are important for cosmology because they trace the distribution of dark matter. The amount and distribution of dark matter in clusters provide constraints on cosmological models. This helps improve our understanding of the universe's composition and structure. Superclusters provide a context for studying the cosmic web. By examining the connections between galaxy clusters within superclusters, astronomers can learn about the large-scale distribution of matter. This research sheds light on how matter is distributed throughout the universe. In summary, galaxy clusters and superclusters are essential components of the universe's large-scale structure. They provide crucial insights into the behavior of dark matter, the influence of dark energy, and the processes that shape galaxies. Ongoing observations and studies of these immense structures continue to expand our understanding of the cosmos. Void regions are vast empty spaces between the filaments of the cosmic web. These regions contain very few galaxies compared to the dense, interconnected filaments. Voids make up a significant portion of the universe's volume. Voids are formed by the gravitational pull of surrounding filaments and clusters. As matter is drawn towards these denser regions, the spaces in between become more empty. This process creates large, underdense areas known as voids. The largest voids can span hundreds of millions of light-years. These immense empty spaces are some of the least dense areas in the universe. Studying voids helps us understand the large-scale structure and distribution of matter. Despite their emptiness, voids are not completely devoid of matter. They contain a few galaxies, as well as dark matter and sparse gas. The properties of galaxies within voids can differ significantly from those in denser regions. Galaxies in voids tend to be smaller and less evolved. They experience fewer interactions with other galaxies, leading to different evolutionary paths. Observing these galaxies provides insights into how environment influences galaxy formation and growth. Voids can be detected through large-scale galaxy surveys. By mapping the positions of millions of galaxies, astronomers can identify the underdense regions. These maps reveal the intricate network of voids and filaments that make up the cosmic web. The study of voids contributes to our understanding of dark energy. The expansion rate within voids can provide clues about the influence of dark energy on cosmic structures. This information helps refine models of the universe's expansion. Voids also offer a unique environment for testing theories of gravity. The low-density conditions in voids amplify the effects of any deviations from general relativity. Studying these regions can help test alternative theories of gravity. Cosmic microwave background radiation interacts with the matter in voids, creating observable effects. These interactions provide additional information about the properties of voids and the distribution of matter in the universe. Voids have an impact on the propagation of light. Light passing through a void is subject to less gravitational lensing compared to denser regions. This effect can influence observations of distant objects and the measurement of cosmic distances. The distribution and size of voids can provide constraints on cosmological models. Comparing the observed voids with simulations helps test theories of the universe's formation and evolution. These comparisons are crucial for refining our understanding of the cosmos. Voids are relatively young structures compared to dense clusters. Their formation and evolution provide insights into the timeline of cosmic development. Studying voids helps piece together the history of the universe's large-scale structure. The dynamics within voids are influenced by the surrounding filaments and clusters. These interactions can cause subtle flows of matter into or out of the voids. Understanding these dynamics helps build a complete picture of cosmic evolution. Future surveys and observations aim to map voids in even greater detail. Advanced telescopes and instruments will provide more precise data on the distribution of galaxies and matter in voids. These efforts will enhance our knowledge of the universe's structure. In summary, void regions are vast, empty spaces that play a crucial role in the large-scale structure of the universe. Studying these underdense areas provides valuable insights into galaxy formation, dark energy, and the fundamental properties of the cosmos. Ongoing research continues to reveal the importance of voids in understanding the universe. The formation and evolution of cosmic structures begin with small density fluctuations in the early universe. These fluctuations, observed in the cosmic microwave background, served as the seeds for all subsequent structures. Over time, gravity amplified these fluctuations, leading to the formation of galaxies and clusters. Dark matter played a crucial role in this process. It provided the necessary gravitational pull to attract normal matter, facilitating the formation of the first stars and galaxies. Without dark matter, the universe's structure would be vastly different. The first structures to form were small proto-galaxies. These early galaxies merged over time to form larger galaxies. This hierarchical merging process continues to shape the universe, leading to the complex structures we observe today. Galaxy clusters formed as gravity pulled galaxies together into dense regions. These clusters are the largest gravitationally bound structures in the universe. The dynamics within clusters reveal important information about dark matter and the universe's overall mass distribution. Superclusters, composed of multiple galaxy clusters, are among the largest structures in the universe. They are not gravitationally bound, but represent regions where clusters are relatively close together. Studying superclusters helps us understand the large-scale structure of the cosmos. The formation of the cosmic web, with its filaments and voids, was driven by gravity and dark matter. Filaments formed along the paths where matter was most densely concentrated. These filaments connect clusters and superclusters, creating a vast network. Galaxies within filaments tend to be larger and more evolved due to frequent interactions. These interactions can trigger star formation and lead to the merging of galaxies. The cosmic web structure influences the evolutionary paths of galaxies. Void regions, by contrast, formed as matter was pulled away into denser regions. These underdense areas contain fewer galaxies, which often have different properties compared to those in clusters. Studying voids provides insights into the effects of cosmic environment on galaxy evolution. The growth of structures is influenced by dark energy, which accelerates the universe's expansion. This acceleration affects the rate at which structures form and evolve. Understanding dark energy's impact is crucial for a complete picture of cosmic evolution. Galactic collisions and mergers are significant events in the evolution of galaxies. These interactions can lead to the formation of elliptical galaxies and trigger bursts of star formation. Observing these processes helps us understand how galaxies change over time. The role of supermassive black holes in galaxy evolution is also important. These black holes, found at the centers of most galaxies, can influence star formation and the distribution of matter. Their growth and activity are closely linked to the evolution of their host galaxies. Star formation within galaxies follows specific patterns, influenced by the availability of gas and the presence of massive stars. The rate of star formation can vary widely between different regions and epochs. Understanding these patterns sheds light on the life cycle of galaxies. Cosmic feedback mechanisms, such as supernova explosions and black hole jets, play a role in regulating star formation. These processes can heat and expel gas, preventing it from collapsing to form new stars. Feedback mechanisms are essential for maintaining the balance within galaxies. Advancements in observational technology, such as the James Webb Space Telescope, will provide deeper insights into the formation and evolution of structures. These tools will allow astronomers to observe the earliest galaxies and the processes that shaped them. Future observations will continue to refine our understanding of cosmic history. In summary, the formation and evolution of cosmic structures are driven by gravity, dark matter, and dark energy. From small fluctuations in the early universe to the complex web of galaxies and clusters, these processes shape the universe's large-scale structure. Ongoing research and advanced observations continue to uncover the intricacies of cosmic evolution. Mapping the large-scale structure of the universe is essential for understanding its composition and evolution. Large galaxy surveys are conducted to chart the distribution of galaxies over vast distances. These surveys reveal the intricate network of filaments, clusters, and voids that make up the cosmic web. The Sloan Digital Sky Survey, SDSS, is one of the most comprehensive efforts to map the universe. It has measured the positions and redshifts of millions of galaxies, providing a detailed three-dimensional map of the cosmos. This data helps astronomers study the distribution of dark matter and the expansion of the universe. Redshift measurements are crucial for mapping large-scale structures. By determining how much the light from galaxies has been stretched, astronomers can calculate their distances and positions. This technique allows the construction of three-dimensional maps of the universe. Gravitational lensing offers another method for mapping the distribution of dark matter. The bending of light by massive objects reveals the presence of dark matter, even when it is not directly visible. This method helps create detailed maps of dark matter's influence on large scales. Baryon acoustic oscillations, BAOs, provide a standard ruler for measuring cosmic distances. These regular, periodic fluctuations in the density of visible matter offer a way to map the universe's large-scale structure. Observing BAOs helps refine our understanding of dark energy and the expansion rate. The study of the cosmic microwave background, CMB, is also vital for mapping large-scale structures. Variations in the CMB provide a snapshot of the early universe, showing the seeds of future structures. This information helps trace the growth of galaxies and clusters over time. Large-scale surveys like the Dark Energy Survey, DES, focus on understanding dark energy's role in the universe's expansion. By mapping the distribution of galaxies and galaxy clusters, DES helps study how dark energy influences cosmic structures. These surveys contribute to our knowledge of the universe's fate. Advanced telescopes, such as the Euclid satellite, will enhance our ability to map the universe. Euclid will survey billions of galaxies, providing precise measurements of their shapes, distances, and redshifts. This mission will offer new insights into dark matter and dark energy. Mapping the large-scale structure also involves studying galaxy clusters. Clusters are the densest regions of the cosmic web, and their distribution provides important information about dark matter and cosmic evolution. Observations of clusters help refine models of the universe's structure. Voids, the vast empty regions between filaments, are also mapped to understand the distribution of matter. Studying voids provides a contrast to the dense regions, offering insights into the universe's large-scale dynamics. This helps build a complete picture of cosmic structure. Simulations of the universe's evolution are used to compare with observational data. These simulations model the formation of structures under different conditions, helping to test and refine cosmological theories. Comparing real maps with simulated ones validates our understanding of cosmic processes. The combination of different mapping techniques provides a comprehensive view of the universe. Optical surveys, radio observations, and gravitational lensing all contribute unique data. Integrating these methods allows for a more detailed and accurate map of the cosmos. Future surveys and instruments will push the boundaries of our mapping capabilities. Projects like the Large Synoptic Survey Telescope, LSST, will observe the entire sky, providing a dynamic map of the universe over time. These efforts will reveal even more about the structure and evolution of the cosmos. Mapping the large-scale structure is not just about cataloging galaxies. It is about understanding the underlying forces that shape the universe. This research provides insights into the nature of dark matter, dark energy, and the fundamental laws of physics. It connects the smallest particles to the largest cosmic structures. In summary, mapping the large-scale structure of the universe is a crucial endeavor in cosmology. It involves large surveys, redshift measurements, gravitational lensing, and advanced simulations. These efforts help us understand the distribution of matter and the forces shaping the cosmos, revealing the universe's intricate and vast network. We've covered a vast and fascinating journey through the cosmos, exploring some of the most profound concepts in modern astrophysics and cosmology. From the origins of the universe with the Big Bang to the mysterious forces of dark matter and dark energy, our understanding of the universe has grown tremendously over the past few decades. We began by discussing the Big Bang theory, the foundation of modern cosmology, explaining how the universe has expanded from a hot, dense state to its current form. We then delved into cosmic inflation, a rapid expansion that occurred fractions of a second after the Big Bang, shaping the large-scale structure of the universe. Next, we explored the formation of the first elements during nucleosynthesis and the conditions of the early universe. These elements laid the groundwork for the formation of stars, galaxies, and eventually, the complex structures we observe today. We also examined the various types of black holes, including stellar mass, supermassive and intermediate mass black holes, along with their significant impact on galactic evolution. These cosmic giants play a crucial role in shaping galaxies and influencing their development through feedback mechanisms. The concept of dark matter and dark energy was another critical topic. While dark matter provides the unseen scaffolding that holds galaxies together, dark energy is driving the accelerated expansion of the universe. Understanding these mysterious components is essential for a complete picture of the cosmos. We also touched on the structure of the observable universe, from the intricate cosmic web to the vast void regions. Mapping these structures helps us understand the distribution of matter and the forces at play on the largest scales. Human observation and technological advancements have been pivotal in these discoveries. From ground-based telescopes to space missions like the Hubble Space Telescope, our tools have allowed us to peer deeper into the universe than ever before, uncovering its secrets and expanding our knowledge. The philosophical implications of these discoveries remind us of our place in the universe. The vastness and complexity of the cosmos challenge our understanding of reality and our role within it, inspiring awe and curiosity. In exploring the potential end scenarios of the universe, we discuss the possibilities of heat death, the Big Crunch, and the Big Rip. Each scenario presents a different vision of the future, driven by the properties of dark energy and the overall dynamics of cosmic expansion. Finally, the importance of predictions and simulations in cosmology cannot be overstated. These models help us test our theories, refine our understanding, and make new predictions about the universe's future, ensuring that our quest for knowledge continues. Thank you for joining us on this journey through the cosmos. If you enjoyed this video, please like and subscribe to our channel for more fascinating content about the universe. Be sure to check out the rest of our videos for more in-depth explorations of the wonders of space.